So the recording is started now. We can go ahead and get into this practice exam. So this is extra practice exam 1, right? This is the one that I have uploaded on Google Drive. You can find the Google Drive in the Discord under the 132 resources channel. I will go ahead and repost like an announcement for it if people are missing it. And then this stuff will be recorded, right, and uploaded to YouTube within like an hour or two after the session. And then the last thing is I've looked at some programs that can like use AI to transcribe like your video or your audio. So I'm going to go and try that at the end of the session to upload this video and have like a decent transcript of what's going on, because then you can just like, if you're wanting to skip towards like one specific section of the review, you can probably look for what you're I guess confused about, so you can just like search keywords and stuff, which would be really nice. And I can upload that transcript, or at least I hope I can upload that transcript to the Google Drive as well, so you guys can search through exactly what was said throughout the session. But no promises that that is gonna 100% work, because I haven't like fully tested it out yet, but I'm cautiously optimistic. So, okay. Let's go ahead and look at problem 1, sheet charges. Hopefully everyone is on that same problem and you guys are on the same practice exam document as I am, but yeah. So problem 1, sheet charges, 3 points. It says 2 parallel sheets have surface charge densities equal to 2 microcoulombs per meter squared for that first one, and negative 6 microcoulombs per meter squared for the second one, right? It says which drawing accurately represents electric field magnitude and direction in zones A, B, and C, right? So it says circle a letter corresponding to your choice and then briefly explain your choice as well, right? So you have all these different options here, A, B, C, and D, with the 2 surface charge densities right there, right? They don't give you an indication of like a point charge or like a test charge or anything like that. They're just giving you these surface charge densities, and they're wanting you to figure out how the electric field lines are going to point, right, and their magnitude. Now, remember with regards to like the magnitude idea here, so for magnitude of electric fields, you are going to be able to discern that from how far the electric field lines are spaced from each other, right? So closer together electric field lines will mean that there's a stronger electric field in that section or area, right? Electric field lines that are more spaced out are going to be weaker electric field lines, right? Now, what do I want to say? So in that case, that's one kind of condition that we're looking for, or one kind of thing that we're keeping an eye out, is the distance between the electric field lines as well as the directions like I mentioned earlier, right? So depending on whether it's a positive or negative like surface charge, it'll have electric field lines pointing one way or the other, right? And so those are 2 things to keep an eye out, as well as how the electric field lines are drawn in terms of like, okay, are they curved lines? Are they just regular straight lines? What's going on here, right? So with all of that being said, there is one thing that we can do right away, right? And that is look at how these electric field lines are drawn, right? So you have A, which is kind of drawn. I'll just label this as problem 1, right? So A, you have surface charge here, surface charge there. This is the positive one, this is the negative one, and you have lines that are more spaced out, kind of like this, lines that are more spaced out like that, and you have really close together lines like this in the middle, right? That's A. And B, sorry, I just have to make sure I write this up because I'm going to upload this document later as well, so people can kind of see what's going on. And then the B, you have everything kind of close together in the middle. You only have 2 lines on the left kind of spaced out, and then lines kind of close together here, pointing to the left. C, kind of similar to A, except everything's kind of switched. The directions are kind of switched. So you have spread out lines like this, but to the left. Close together lines like that, but to the left instead of to the right. And then you also have spread out lines like this to the left, right? And then D is kind of weird because you now have no lines on the outside of the charges, right? Or the surface charges, but you have like these curved lines, right? That, I don't know, yeah, let me draw it like this. So they're kind of curved in that sense. So in this case, which one do you think we can eliminate pretty easily here? D, right? So this one is kind of way off, right? Because the electric field line should be there kind of straight, perpendicular to the surface charge densities. They should not be curved like that. And at the same time, it's like we also have to consider now the second part, second filter kind of with this question, which is looking at the positive and negative surface charge and then figuring out, okay, well, am I going to be seeing charges on the outside here or not, right? So we have a surface charge density of 2 and negative 6, right? So we said this left one was positive, right one was negative. If you remember for electric field, for surface charge, right, what was that again? Can somebody tell me what the electric field for a surface charge is? Or for a sheet charge? And if you don't remember, it's fine. Like, I can just write it down. I'm just wondering if someone knows it off the top of their head. Yep, so sigma divided by 2, and then that constant, right? The permittivity constant. So 2, or my bad, actually it's, yeah, my bad. Sigma over 2 times the permittivity constant, right? So what do you notice here about the electric field? It's not dependent on the distance you are away from the surface charge or the sheet charge, right? So the magnitudes, right, are going to be dependent on just the sigma, right? Because we have positive 2 and we have a negative 6, right? So it doesn't matter if we're far away over here from the negative charge or far away here from the positive charge. That doesn't matter, right? If we were to essentially just look at one of those surface charges, right? If we were to look at one of those surface charges, what we'll see is that any distance away from the surface charge, you're going to have the same magnitude of your electric field, right? Now, we can try and figure out the net electric field here, right? So we have positive 2 and negative 6 microcoulombs per meter squared, right? So let's try and figure out E net here. Now, when we're looking at this, we have to realize that a lot of the times you are going to be looking at a positive test charge as your convention, right? That's usually the charge that we're kind of looking at to test things. And so if I were to put a positive charge here, how would that react to the electric fields? Can someone describe how it would react to each surface charge? Excellent. So in terms of the positive sheet, it would be repelled, so it would move to the left. How about the negative sheet? Exactly, right? Now, you essentially have a positive x direction and a negative x direction here, right? So if we look at this being what? Honestly, I can just get rid of the permittivity constant and the 2 at the bottom here. I can just say negative 6 And then, what was I going to say? Minus 2, right? Is that what I want to do? Hold up. Nah, my bad. 2 minus 6, that's what I want to do. Yeah, 2 minus 6. Yeah. So negative 4 is your overall net electric field, right? Negative 4 is your net electric field here. That's what I want to do. I want to figure out just the electric field net in general. Now, that tells us that the net electric field is going to be a negative kind of value here, right? So you should see that the pull from the negative surface charge is going to be stronger than the pull from the positive, or the repulsion from the positive surface charge. So we should see that this pull from the negative should be greater than the repulsion from the positive, right? But it's affected. It's affected by it, right? So we should see here that the lines on the outside to the left of the surface charge, this positive surface charge, they should be spaced out and they should be to the right. Like we said, the net electric field is going to be a negative 4, right? So everything's going to be kind of pointing towards that negative surface charge. Everything's going to be pointing towards the negative surface charge. So that right there, finding out the net electric field, is going to eliminate C, and should also eliminate B if you were to just look at the net electric field there. Because we want everything to kind of point towards that negative surface charge right there, right? So when you have that negative net electric field, we want the field lines outside the sheets to point inwards towards that negative surface charge, right? And so now it's a matter of looking at like the magnitudes. Even if let's say if we didn't like cancel these out, C and D, we want to look at the magnitudes as well. Because the magnitudes here, you should see a much stronger electric field in the middle between them, because you can kind of think about it as if I placed a positive test charge here, well, it'll get repelled by that positive surface charge, and it'll also want to move towards the negative surface charge. So there's a very strong electric field to the right. You see what I mean? Now, if I put a positive test charge over here, it's going to want to get repelled by that positive surface charge, but it's also attracted to the left by the negative surface charge. So that's why on the right here, the arrows should be pointing to the left, and they're more spaced out because there's this extra repulsion by the positive surface charge, right? So you have to account for the directions, account for the magnitudes, right? So, and this is all assuming, right, a positive test charge. Does that make sense? Okay. And you could say as well, even if you didn't want to look at the positive test charge, because the positive test charge is the convention, you could literally just look at what electric field lines, like how electric field lines point with respect to positive and negative surface charges. So, positive source charges or surface charges will have their electric field lines pointing outwards, while negative surface charges or negative source charges or negative surface charges will have their electric field lines pointing inwards, right? So if I were to take this, look at it again, this is positive, this is negative, then electric field lines with respect to each one on its own should be this way and this way for positive, this way and this way for negative, right? That's how the electric field lines would point on either side of the surface charges individually. But once again, if I calculate that E net, the net electric field, it's net negative 4, right? So the net pull there is from that negative surface charge, right? So in this case, you see here this left arrow that would be the individual line right there, or electric field line for that surface charge. But because this negative is so much stronger, right, because it has that larger surface charge density, it's going to pull it more, right? And so this, what would normally be pointing to the left, is going to point to the right, but at less magnitude. And then we have here, what would point to the right continues to point to the right, because here in the middle, you have two arrows pointing to the right, so they get stronger, so they get closer together, greater magnitude. Here on the outside, you would normally have the arrow pointing to the left. Well, it's pointing to the left. Negative surface charge is pretty strong. There's also positive surface charge is going to be repelling it, right, or having that, if we extended that arrow this way, then you could see it kind of detracts from it. So we should see still pointing to the left because that negative surface charge is going to be stronger, but slightly less magnitude, a little bit more spaced out. Hopefully that also clears it up there. So the net electric field in this case essentially changes the usual convention of the positive lines always pointing out. Exactly, right? So based on the net electric field, it'll change the usual convention. Because otherwise, like I said, if you looked at either side of the surface charge, the positive one, they should both be kind of repelling or pointing outwards from the positive charges. If you look at a negative surface charge, everything should be pointing towards it, right? Now you then have to take into account how the net electric field is, and then adjust your lengths, or not your lengths, but how everything is spaced out, right? Because that'll be the magnitude, and then directions, right? So does that make sense? Okay, awesome. So that's problem 1. Problem 2 is going to be 3 charges are arranged as shown. What is the charge Q3 such that the net force on Q2 is 0? Okay, so we have a negative charge here on the left, a positive charge here on the right. This is Q1, this is Q2, this is negative 8 nanocoulombs, this is positive 1 nanocoulombs, right? And we have this Q3 here on the left that we're not sure about. The distance between Q2 and Q3 is 5 centimeters. 5 centimeters. And then this here, distance between Q1 and Q2, is 10 centimeters, right? Now, they want us to figure out what is the charge on Q3, such that the net force on Q2 is 0. So this is kind of going back to the stuff that I had on my slides as to how to define what the force on something is, right? So here's this notation again. Net force on Q2. What does that mean? Something on Q2, right? Something on Q2. So, by something else, right? So this is the force on Q2 by some other charge, right? So either by Q1 or by Q3. What does this notation mean? You can kind of flip it. You can say, okay, well, it's how Q2 will react to Q1 or Q3, right? It's how Q2 will react to Q1 or Q3. Is it going to go to the left? It's going to be attracted to it, right? Going to go to the right, going to be repelled to it. What's the deal? So, if I were to ask you how Q2 reacts to Q1, what would you say? What direction would we move in? To the left. It's going to be attracted, right? Because we have a positive charge for Q2 and a negative charge for Q1. So it's going to react to Q1 by moving towards it, to the left, right? So force on Q2 generated by Q1, right? So Q1, because it's there, it's present, it's going to attract Q2. Q2 is going to react to Q1. Q2 is going to react to Q1. So that force we label as force of Q1 on Q2. It's how Q2 reacts to Q1. Well, how does... Yeah, go ahead. So if this was another positive here, yeah, so if this... Yeah, go ahead, sorry. Okay. Yeah, if it was positive, same deal, right? So how does Q2 react to Q1? Well, since they're two positive charges, they're going to be repelled, right? So Q2 will want to get far away from Q1. So it's going to move to the right. So if I said Q2 reacts to Q1, it would still be the force of Q1 on Q2. Q2 reacts to Q1 by moving to the right. Mm-hmm. So, and what I like to do, and if you notice the equation here for the electrostatic force, Q1 and Q2, you only take the magnitudes of those. Only apply the direction afterwards. When you set up your net force equation, then attach negative signs based on if it's moving to the left or if it's moving to the right or whatever, right? Otherwise, make sure to keep your like magnitudes there, right? Otherwise, you're going to throw things off a little bit. But yeah. So Q2 reacts to Q3. Well, if we already said that Q2 is going to move to the left to be attracted to Q1, if I wanted this charge, Q2, not to move at all, right? Because net force 0 means it's not going to be moving. If I don't want it to move, what should the charge of Q3 be? Yeah, like positive or negative, that's what I mean. Yep. So if this is negative, well then the positive charge here is also going to be attracted to it, right? So it's going to be pulled to the left. So it's like a tug of war between the two. So Q2 is going to want to react to Q1 by moving to the left, but it's also going to want to react to Q3 by moving to the right. So that's how we're going to look at things here. So we know that Q2 will react to Q3, and that's going to be the force of Q3 on Q2. Just by looking at how we've arranged this, we can see that this force, Q1 on Q2, this is going to be negative, right, technically, if we were to not do things in magnitudes. And this should be positive, because one is to the left, one is to the right. So if we're setting up a net force equation, F net, it should kind of look like F Q3 on Q2, because that's to the right, minus F Q1 on Q2, and that should equal 0, because we want the net force to be 0. And then you can set them equal to each other, right? So you'll see that this is KQ3 Q2 over R squared, and equal to KQ1 Q2 over R squared, right? That's the electrostatic force equation. And I set them equal to each other because I added this one over here, right? Let me just draw that out. And then from here, you basically just plug in your values, right? So K is at 9 times 10 to the 9th, newtons times meters squared over coulomb squared. So K is 9 times 10 to the 9th. Q3 is just the charge of Q3. Or, we don't know it yet, so Q3 unknown. Q1 is that negative 8 nanocoulombs, right? So this is 8 times 10 to the negative 9. And Q2 is 1 times 10 to the negative 9, because it's nanocoulombs. And we want things to be in coulombs because SI units and stuff. So if we were to plug everything in, right? And like I said, if we're using magnitudes, then what should happen is that we end up with the magnitude of Q2, or of Q3, my bad. So Q2, if we plug it in as positive, Q1, we plug it in as positive, right? We just take the magnitudes of everything. I also forgot that R for this one is R23, so the distance between Q2 and Q3, and this is R12, the distance between Q1 and Q2. So R12 is that 10 centimeters, or 0.1 meters, and then R23 is going to be that 5 centimeters, or that 0.05 meters, right? And then you can just plug that in and square it. Don't forget to square it, because I did on my exam, and sadly I lost points for that. So this is R squared for this electric force equation, right? Yeah, like I said, if you just plug everything in, you should get the magnitude, once again, of Q3. So this will give you the absolute value of Q3 when you get it. And I think you should get, let me double check here. I think it's -2 nanocoulombs, right? Or basically -2 times, well, not negative, so just, oops, let me erase this. So it should be just 2 times 10 to the -9, or 2 nanocoulombs, right? That's your magnitude. However, for the problem, they didn't ask for a magnitude, right? They didn't ask for a magnitude here. And so, in this case, you could just assign the negative sign afterwards, because we figured it out from a logical perspective anyway. Otherwise, what you can do is, if you wanted to play it dangerous, you could plug in the values, like I said, for the charges. You can add the signs in, but I think that's, like I said, is playing it a little too dangerous. I would rather set everything up in magnitudes and then add my sign at the end based on the logic that I know, like how things are going to get repelled or attracted to each other, right? So I figure out the logic of the problem first. How are things going to move, right? And then just make sure I plug in the magnitudes. And I know that at the end I have my magnitude. If the question is asking for magnitude, perfect. If it's not, right, or if it just doesn't say magnitude, then assume you have to assign the charge, and then just look at what that charge could be based on, like I said, how things are going to react to each other, right? So we already figured out that Q3 has to be negative, right? It has to be negative, because if the Q2 is positive and it's attracted to the Q1, which is negative, it's going to move to the left. So in order to have that leftward motion be canceled out, we have to have a motion to the right. Well, how does the positive charge Q2 move to the right? Well, if there was a negative charge Q3 to the right of it, it's going to be attracted to it to move to the right. So figure out the logic first, do your net force with magnitudes only. You're going to end up with a magnitude as your answer. Assign the signs at the end. I think that's probably the best bet to do that, to avoid any confusion, because I think part of the reason why I lost points on mine was that I screwed up my answer a little bit because of the signs. But yeah. Does that make sense for problem 2? Yeah, go ahead. Well, if you're using for like electric potential for volts, like that would just give you the net electric potential, but they're asking for net force to be 0. So those are that would be a little different. In fact, like what I did on accident is, now that I'm looking at my work, right, I actually forgot to square the radius at the bottom, so I think that was actually my issue. It wasn't that, like, I think I had my signs actually correct, even though I played it dangerous by assigning the signs to begin with. But yeah, I forgot to square my radius. So yeah, every equation is kind of like in its own thing, and there's like a style or way how to solve each of these problems. So yeah, if they're asking for net force, just stick with the net force equation. I wouldn't try to like jump bridges and try to figure things out that way, because I mean either way, like if you try to do it with electric potential, like I don't understand why you would do that, because you're trying to figure out net force, you're not trying to figure out electric potential, because if you do that, V equals KQ1 Q2 over R or whatever, right, then you're just gonna figure out what the net electric potential is, and that's it. And yeah, I mean, yeah, so I don't know. Yep. So that's problem 2. Any other questions about problem 2? Nothing? Okay. Problem 3 then. Oops. problem 3. We're looking at capacitor was built with an insulator of dielectric constant kappa equals 4 between its plates. With the dielectric, the capacitance of the capacitor is 10 microfarads. It's charged to a total charge of 30 microcoulombs and then is disconnected from the battery. Then the dielectric is then removed. So part A is asking, calculate the final capacitance of the capacitor, right? So capacitance final, or we can say capacitance with dielectric, right? How do you figure out the new capacitance, right, after you put it in a dielectric? How do you do that? What's the equation for that? Because that's essentially what they're asking, right? So it's the final capacitance of the capacitor is just going to be the capacitance with the dielectric inserted in between. Any ideas how to approach this? Yep. Exactly. So you take your kappa, right, your dielectric constant, multiply it by your original capacitance. That'll give you, it's like inserting a dielectric is going to be amplifying the capaciting power, if that's a word, for the capacitor, right? So essentially what you're going to do here is just multiply that dielectric constant by the, actually hold up, I think I messed it up. So this is right, the equation is right, but the capacitance with the dielectric is already given. I messed it up. So capacitance with dielectric, they said with the dielectric, the capacitance of the capacitor is 10 microfarads. So that's your capacitance with dielectric, right? Kappa is my 4, that's my dielectric constant. This C is without the dielectric, which is exactly what I'm trying to find, right? And so to amend my initial statement, the final capacitance of the capacitor is not when the dielectric is inserted, it's that final sentence. It's when the dielectric is removed, right? So when we remove the dielectric, what happens to the capacitance, right? So we know that the capacitance was initially amplified by taking the original capacitor times the dielectric constant. So now we're trying to figure out, okay, well, if I remove it, what would be my pure capacitance, basically? My capacitance without my dielectric. So that would be 10 microfarads divided by 4, and that gives me 2.5 microfarads. That's my capacitance without the dielectric, because remember it says at the very end, the dielectric is removed. And you can see from the diagram, it has that little green insulator in the middle, and then by the end, it's removed, right? So you started off with the dielectric with a capacitance of 10 microfarads, right? And you ended up with basically some pure capacitance without the dielectric. And so we know the equation is capacitance with the dielectric is going to be equal to the dielectric constant times the capacitance without the dielectric. And so capacitance without the dielectric is exactly what we're looking for, because that's the end point, and so that's 2.5 microfarads. For B, it says calculate the final voltage in the capacitor. Well, it says it's the capacitor is charged to a total charge of 30 microcoulombs, and then once it's charged up, it's disconnected from the battery, and then the dielectric is removed afterwards, right? So what we're looking for is Q without the dielectric, right? Q without the dielectric is going to have that 30 microcoulomb charge, right? 30 microcoulombs is the charge without the dielectric, because that'll be the point where we've charged it up and we remove the battery, right? Now, we know the capacitance without the dielectric as well. That is the 2.5 microfarads. That's the capacitance without the dielectric. Remember, we're looking for things to be without the dielectric because this is the end point, right? It's the final voltage, the final capacitance. It's when everything has been disconnected, right? So everything without the dielectric, without the battery, right? And now we're looking for voltage, final. So there's an equation that will relate all these values together, and that's Q equals CV, right? So there's some Q, some charge that's present without the dielectric, some capacitance without the dielectric, and then we want to figure out the voltage that's stored, or the voltage there in the capacitor, right? So 30 microcoulombs, and then we have, you can divide it by 2.5 microfarads, and that gives us our voltage, and our final voltage should be 1.2 volts. If you want, you could have converted microcoulombs to well, just coulombs, right? So 30 times 10 to the negative 6 and 2.5 times 10 to the negative 6. So micro, just make it SI units. But you'll see 10 to the negative 6 is on top and the bottom, so it cancels out. So you can just do 30 divided by 2.5, I think, right? No, hold up. So that's not 1.2 volts, my bad. I don't know why I put 1.2 volts. 12 volts. So I think I just did 30 divided by 25. So this is 12 volts. So 30 divided by 2.5, 12 volts, that's the final voltage of the capacitor, right? So with this capacitor stuff, and you'll probably see an example of this on the exam. I'm betting that this is going to happen. So I don't know how to start this exactly because I'm just going to be like teaching some stuff here. So if you have a battery connected to that capacitor there, right? Let me draw it this way. So this battery right here connected to the capacitor. So as long as that battery is connected, right? As long as the battery is connected, your voltage is constant. So if I had removed the dielectric and I kept the battery connected, I would still be experiencing 12 volts. Let's say the battery was originally 12 volts, right? I have this dielectric here. Okay. Well, if I remove it, I have no dielectric in the middle now, and I still have this battery here. As long as the battery's still connected, it maintains that constant 12 volts. Well, think about it. If I maintained the battery connection and I went back and calculated something, right? What if I calculated what I have? I know Q equals CV, right? I know Q equals CV. Well, 12 volts, that's my voltage, C, Q, right? So with my capacitor now, right, I have removed the dielectric constant, or the dielectric, right? So I went from 10 microfarads to 2.5. So you see here if I did 2.5, and then times 12, that gives me the 30 microcoulombs there, right, for my charge. Now, I wanted to like explain something here. I can't remember what I was going to say. Hold up. I know. Okay, so just because I can't think of what the problem was asking off the top of my head, it was a quiz problem that I uploaded to the Google Drive. I think it was week 10. Yeah, so week 10 stuff. It's extra practice. Let me pull it up here, just so that I'm not like going on a rant and being confusing. So the nature of the problem was that, okay, I have battery connected to the capacitor. It says while the capacitor is connected to the battery, right? While the capacitor is connected to the battery, the distance between the two plates is doubled, right? So if I were to increase the distance between the capacitor plates, the question is, how does the voltage V, charge Q, and capacitance change, right? So that's the question that I was thinking of, my bad. So forget what I was talking about here. So if I wanted to basically like increase the distance between the two plates, that's what I was thinking of, right? If I wanted to increase the distance between the two plates while keeping the battery connected, right? What change should I see to the voltage, charge, and capacitance? So voltage, charge, capacitance, right? So with respect to the voltage is going to remain constant because you're still connecting that battery and it's still providing a constant voltage there. If I look at the charge, well, based on Q equals CV, right? There's going to be a relationship between the voltage, not between the voltage and the charge because the voltage is constant, right? But perhaps between the capacitance and the charge, right? So what happens to the capacitance? Because if we double the distance of the plate, well, we know that capacitance, there's an equation for it, and that's the permittivity constant times A over D. So the area of the plates divided by the distance between them, and then multiplied by the permittivity constant. Well, if I doubled the distance between them, then I halve the capacitance. So this is 1/2 capacitance. So this is 1/2 capacitance here times the same amount of voltage, right? Then I've effectively halved the Q as well. An alternate problem is if we had disconnected the capacitor from the battery, right? So if we remove this connection here before doubling the distance, so we remove the battery and then we double the distance, then how does the voltage, charge, and the capacitance change? Well, voltage would not be the same anymore because we don't have that constant source of voltage from the battery. We want to figure out charge, we want to figure out capacitance. Well, charge has to remain the same, right? Charge has to be constant. There has to be a constant amount of charge stored there in the capacitor. So Q is Q. Capacitance, we already said, it would be halved because we multiplied, or we doubled the distance of the capacitor, right? Once again, Q equals CV. Well, if we halved the capacitance, we want to figure out the voltage, and the Q is the same. Well, if you multiply over the 2Q equals CV, right? And then 2Q over C equals V. Well, we know that if we were to rearrange this original equation, Q over C equals V, 2Q over C equals V, well, we've doubled the voltage now, right? So we've doubled the voltage in this case. So understanding the relationship of like what happens if I disconnect the battery, if I double the distance of the capacitor, if I disconnect first, then double the distance, or if I double the distance and then disconnect, understand like what happens in each case, right? So if I disconnected the battery first and then double the capacitance, I should be seeing something like this, right? Where the voltage is now no longer constant because I've disconnected first, and then I've doubled the capacitance. So my voltage would change. My charge remains the same because it's a conservation of charge. But if I had doubled the distance first, right? If I doubled the distance first while maintaining a constant voltage, then voltage is the same, capacitance would be halved, charge would be halved based on this relationship here. So hopefully that was kind of a good example problem just to kind of see what was going on there. Does that make sense so far? Okay. And that example problem, like I said, is on the Google Drive. It's practice problems under week 10 folder. Okay, so we can move on to problem 4. Any other questions about problem 3, by the way? Okay. Problem 4 is where we're going to start to see more of this resistor stuff here. Okay, so problem 4 is In the arrangement of resistors shown the current is I1 equals 2 amps. It says part A, determine the currents I2 and I3, right? So, I'm going to draw this out real quick. So we have not straight, but it's fine. This resistor here, this resistor there, this resistor here, and then current coming in here, right? So when you have resistors that look like this, right, you have a current coming in. Let's say maybe there's a battery here, right, providing some current comes through. Here's this little branch point is what I like to call it, right? Branch point. This branch point is where you would see distribution splitting off of the current. So to explain things in my analogy that I was mentioning earlier about the trees and stuff, so if you were to have a tree, right, you have some roots here at the bottom, whatever, right, this is your battery, the roots are your battery providing that current. This trunk and all the branches that it encompasses will be the battery, right? There's no real room for the resistors in this analogy for some reason. I don't know. Maybe I'm just not thinking of something, but let's just say you find resistors along the wires, right, or along the branches or whatever. So as you move up the trunk, you'll have branches like this, right? These main branches, if I just had a branch that looked like this and that was the end of it, then I could say the trunk is in series with the branch, right? So if I had a resistor here and a resistor there, right, this along this one branch here, you can see everything kind of is consecutive, right? So I go from this resistor to that resistor, trunk to branch, without any extra branching points. They're connected consecutively, they're in series, right? But not all branches are like that, because you'll eventually have a branch that'll branch off into its own little branches, right? So if I had a resistor here and a resistor there, right? Well, I can't quite say, or actually, hold on, let me edit this a little bit. So if I wanted to say if I had a resistor here in the trunk, right? And then let's say I have a resistor here, right? Well, I can't say that this resistor here is in series with this resistor there, because wait, was something wrong with the stream? Okay, all right. Yeah, so if you have that resistor there and that second resistor there on that branch, I can't say that those resistors would be in series because they would have to be consecutively connected together, right? So there has to be no additional branch points getting from that resistor to the second resistor. So you see here that if I move to this branch, right, the current will go this way. But it could also go along this direction here, this second branch here, or it could go here, right? So this idea of branching, where the current can be split off into multiple different directions, is when you would have resistors or even capacitors in parallel, right? So I get to this, here's my battery, here's my roots, here's the initial trunk, right? And now I get to a branch, right? If I ignored this resistor, this would be that one branch that I was talking about here with no extra branch points. It goes right through here, current is constant, comes through it, no distribution of the current, no extra branching points, it's consecutive, that's fine, right? But that's not the case, because I could go through this middle resistor, I could go through the top one, or I could go through the bottom one, right? And so what happens is the current gets split off, right, into I1, I2, and I3. So a little bit goes here, a little bit goes there, a little bit goes there, right? Current will have to be conserved in the end. So these little branches, what I like to call them, so whenever you experience like a little branching point where the current splits off in different directions, then know that those branches, quote unquote, are all going to be in parallel with each other. So I1, I2, and I3 will be in parallel with one another, right? If, for example, I had a resistor here, let's say this call this I4 or something, right? I1 and I4 would be in series because they're connected consecutively. There's no branching of the current. There's no splitting off of the current anywhere between I1 and I4, this section here. Because there's no branching point in between them, there's no splitting off of the current. The current can't go in multiple directions. Those are in series. They're connected consecutively to each other. They're in series. But because the current comes across a branching point where it can go upwards to the left or downwards, right? The current can split off in multiple directions. Then know in each one of those directions, those things are going to be parallel, right? So if I had I1, I4, I2, and I3, right? I can't say, like, I can say, what did I want to, okay. So this whole part, right? This combined like branch right here, because this is technically one branch. Like everything along here is one branch. Everything along there is one branch. Everything along here is another branch, right? Now, this I1 and I4, they're like on the same branch basically, right? So I can't say like I4 on its own is necessarily parallel to I2, right? Can't quite just say that on its own. But what I can say is that I1 and I4 together, they are parallel to I2 and also parallel to I3. That's what I can say, right? And so I1 and I4, like I said, there's no branch point between them. I can add them up in series. Then I can look at a combined resistor called not I14, my bad. I'm saying I and I. It should be R because this is resistors. So if this was R, my bad. So not I, but R. R1, R4 would be the combined resistor, right? R14 would be parallel to R2, would be parallel to R3. R1 and R4 would be in series with each other because they're consecutive. There's no branching off of the current between them, right? So that's the idea here with series and parallel resistors. And so with those series and with those parallel resistors, you'll often see that with that branching point, there is an initial input point, right, where the current comes in, it branches off, and there's a final output point where all of the currents come together and reunite. So if I had 7 amps going in here, 2 might have gone up there, 2 might have gone through the middle, right? And then 3 might have gone down here. Well, 2 will come back down here, 2 will come up there, 3 will come up there, and then 2 will come through the middle. And so you come out with 7 amps once again, right? So there's an input point, output point where they kind of reunite together. So that's your parallel resistors in that sense. And that same thing kind of works with capacitors. Now, we're going to have some problems here in a sec that we'll go over more specifically, like characteristics of all of these and how to add them up and whatnot. But just wanted to kind of quickly just explain that analogy there for the branches and stuff. But does that kind of make sense? You kind of start to understand it a little bit more. Okay. So yeah, going back to part A, basically, it was asking to determine the currents I2 and I3. Well, they told us that I1 is equal to 2 amps, right? I1 is equal to 2 amps. We know that I1, I2, and I3 will have to add up to each other, right? We know that for a fact. But also, in order to solve this problem, we have to understand a very important characteristic of parallel resistors. When you have these resistors in parallel like this, they will all have the same voltage across them. Right? V1 has to equal V2, has to equal V3, right? The reason for that is, like, if we were to have this circuit here where it's these branches together, right? We had a battery in between here, and we had a resistor here, resistor there. Well, there's a certain voltage drop here, certain voltage drop there, right? Let's say the whole thing was 12 volts. All the voltages of all the voltages have to sum up together to equal the voltage of the battery, basically. So this battery is supplying 12 volts. Let's say this was supplying 6. This one was supplying, okay, perfect, whatever, 6 volts, and this is supplying 2 volts, right? So that's 8 volts, right? So we have 4 volts left over. Now, this 4 volts, right, cannot be like split between them. You can't say like, oh, this one has 1 volt, this one has 2 volts, and this one has 1 volt, right? You can't do that. Why? Because in theory, if we were to cut off the others, that resistor has to stand alone. That resistor has to be able to carry everything on its own, right? So if we were to cut off any one of those resistors, we should see still a maintenance of the conservation of the current, right? Conservation of the charge, and the voltage drops should all make sense, right? And so in that case, we know that resistors in parallel will all have the same voltage across them. So this one is going to have 4 volts, this one's going to have 4 volts, this one's going to have 4 volts. They might be different resistance values. They will each carry a different current, right? Because the current is split up at those branch points, but they must have the same voltage because, once again, just kind of jumping forward a little bit, but if you were to find the equivalent resistance, which you've probably gotten some practice with by now, if you find the equivalent resistance and you combine these branches into one big resistor, that big resistor has to equal those 4 remaining volts, right? So that's kind of the idea there. At the same time, if you think about it, they all have the same input point and they all have the same output point, right? And because of that, one end is connected to the positive terminal, one end is connected to the negative terminal of the battery, right? They all have the same connections on either side. And so since they have the same common connection on either side, they should have all of the same voltage on either side, right? Or basically all the same voltages across them. So yeah, voltages will be the same for parallel resistors, right? So like I said, if this is a 6 volt drop, this is a 2 volt drop, you have 4 volts left. 4 volts will not get split up between each resistor. 4 volts is the voltage across every single one of them. This is 4 volts, this is 4 volts, this is 4 volts, right? What differs between them, depending on if the resistors, like if you have 2 resistors at the same resistance, then the current might be the same through them. But what will differ in general is going to be that current, because the current will come in hot here and then get split up to those separate branches and then reunite at the end, right? So voltages will be the same across parallel circuits or parallel resistors, right? But the voltage drops will be different across resistors in series, right? So if we were to combine this into one equivalent resistor, one big one, then that big one would be in series with this one and would be in series with that one, right? And so when they're in series like that, each one will have a unique voltage drop, and they must all add up together to equal the original voltage of the battery, right? So voltages across series circuits, or series resistors, so voltage series, you'll add up the voltage of the first one, voltage of the second one, voltage of the third one, whatever. Voltage of ones in parallel, voltage is equal 1, 2 is equal to 3, right? The voltage will be the same. So series, you would add up the voltage drops. The ones in parallel, they would all have the same voltage as one another, right? And so, in addition to that, right? So I have another question here. So the other relationship of charge being equal when resistors are in series. So that's with capacitors, right? So if we were talking about capacitors in series, right? Or are you still talking about resistors? Because I think if you're talking about resistors, then the charge through series resistors would have to be the same, right? So the idea is that this battery sends out a current, some charge flow per unit time. That's what current is. So it sends out 7 amps, like I said. 7 amps goes through here, passes through that resistor, still 7 amps, right? It hits this branching point. Well, the parallel resistors, you might have 2 amps go up here, 3 amps go down there, another 2 amps go down here. And then they come out, another 7 amps. Goes through this resistor, 7 amps, right? So resistors in series will have the same current. Resistors in parallel will have different currents because they'll be split up. Sometimes though you might have a resistor that's like 2 ohms and this resistor might also be 2 ohms. In that case, they might have the same current across those two resistors, right? In that case, right, like current would be the same, but it's split up, right? So let's say, for example, if I had these 3 resistors, all of them being 2 ohms, right? That's the resistance for each one of them. Well, if my current is 7 amps, right? And I know, for example, that I have, like I said, if I have 6 volts here on the left, 2 volts on the right, so I have 4 volts left. 4 volts has to equal the voltage drop across each resistor. So 4 volts, V equals IR. The resistance here is 2 ohms across each one. Each one will get 2 amps, right? But the idea is that the amps are being split up. So if I add up the current between all of them, remember the current has to add up, right? Because they split off, they must add up at the end. So the current across all of them would be 2 plus 2 plus 2. That's 6 amps. So instead of 7, if I had basically 1 off, right? So 6 amps going in, 2 would go up to the first one, 2 would go through the middle, 2 would go through the bottom one, right? Yes, in that case, they would all have the same current, right? But the current has been split up. That's the idea. The splitting up of the current is when you have resistors in parallel. Does that make sense? But with resistors in series, they must have the current be the same. So resistors, series, current, same. Resistors, parallel, they add up. Not they add up, current adds up. Right? Now, so it's determined currents I2 and I3, right? So we see that there are different resistance values there for each resistor. We have one that's 3 ohms, one that's 6 ohms, one that's 2 ohms, right? So the 3 ohm resistor, or actually let's look at the I2 first, or I1 first, my bad. So I1 has current going through it of 2 amps, right? So I1, 2 amps. The resistor for R1 is 3 ohms, so voltage equals IR, right? That means the voltage is 6 volts, 2 times 3, right? Because we know that these resistors are in parallel, that means what? That the voltages across every single one is going to be the same. So I have 6 volts for that second resistor is equal to I2 with a 6 ohm resistor, so I2 would equal 1 amp. Well, 6 volts once again is equal to I3, and then times 2 ohms for that resistance of that resistor. So I3 is 3 amps, right? So you see here that the voltage across each one is the same. Voltage across each one is the same. Current is going to be split up between them. And then, yeah, that's pretty much it, right? And so if we look to part B now, where it says determine the current entering the circuit. Like we said, this is a branching point. Things are going to get split up, right? So the current has to be conserved. We came in with a certain amount, it gets split up, we have to come out with the same amount, right? So the currents across those resistors in parallel would add up, right? So we have 1 amp. Oops, let me circle things here. So So we have 2 amps for I1, 3 amps for I3, and 1 amp for I2. So 2 plus 3 plus 1 will give us 6 amps, right? So I of the circuit is equal to I1 plus I2 plus I3. Everything has to be conserved, so 2 amps plus 1 amp plus 3 amps, and that's equal to 6 amps. Does that make sense? Any questions? No? Nothing? Okay. Fair enough. Is everything kind of starting to make sense a little bit more with the circuit stuff? Okay. Cool. Problem 5. It says, what is the electric potential at point P indicated in the figure? So we have point P. We have a negative charge here, that's negative 1 nanocoulombs. We have a positive charge here, that's positive 2 nanocoulombs. This distance right here is 3 centimeters. This distance right here is 4 centimeters, right? They're asking for electric potential. Well, electric potential is V, right? That's your voltage. And so voltage, remember the equation for that, is KQ over R, right? The electric potential, if you look at the equation, if you notice that the equation, right, V equals KQ over R, is looking at uppercase Q. So looking at the source charge, right? It's not factoring in the test charge or the point charge, right? So if I said point P was a positive charge, does not matter. I don't factor that one in. Doesn't matter anything like that. I'm just looking at how the electric potential is affected by these source charges relative to that point P, right? So V equals KQ over R, right? Where the source charges are that positive and that negative charge there relative to point P. So simply, if I want to figure out what the basically net electric potential is here, right? Then I should be adding up the electric potential from that positive charge and from that negative charge. Simple as that, right? So if I label this as charge 1 and this is charge 2, this would just essentially be V1 plus V2, right? And so I know K is my 9 times 10 to the 9th. Q would be 2 times 10 to the negative 9th for one of them, and negative 1 times 10 to the negative 9th for the other one, right? My R now, when you're doing these types of problems, your R, your radius, your distance, is going to be the direct distance between that point and the charge. So the direct distance between point P and that negative charge is what? What is the direct distance there? The direct distance between point P and the negative charge. 4, exactly, 4 centimeters, right? That's the direct distance. How about the direct distance between point P and the positive charge? Excellent, right? And that's 5, right? So if this is a 3, 4, 5 triangle, if you're good with geometry, you'll recognize this is a 3, 4, 5 triangle. So this is 5 centimeters. You could also use Pythagorean theorem. 3 squared plus 4 squared is going to give you 5 squared, and your radius in that case would be 5. But these are centimeters. We want to deal with things in meters, right? So it's 0.05 meters, 0.04 meters, right? So KQ over R. K, well, yeah, I'll just write it out. So there's a 9 times 10 to the 9th. That's your K. Times your Q. 2 times 10 to the negative 9th for that positive 1. Divided by the radius for it, which is 0.05. And then we add it to the other electric potential, which is 9 times 10 to the ninth, times the -1 times 10 to the -9 coulomb, right, charge, and then divided by 0.04 meters, right? And then, yeah, you pretty much add those together, and there you go. You have your electric potential there, right? You don't have to do any fancy like cosine sine stuff or anything like that. Simple as that. You just look at the direct distance between them, add them up, no x component, y component stuff or anything like that. So, what do I want to say for this one as well, just to kind of clear something up here. So, no, I think that's it. Yeah. Oh, yeah. Now I remember. So for this one, you don't use like magnitude or absolute value for the charges or anything like that. You add them up. Yep, exactly. Excellent. So no magnitudes, right? So you factor in the charge sign here. Can you explain the difference between little q and large q? So lowercase q is going to be your test charge or your point charge, right? So test charges are, as the name suggests, charges that we are going to be looking at to test the effect of like an electric field or something like that, right? Uppercase Q are your source charges. They're going to be providing the electric field, going to be providing that electric potential, right? So uppercase Q, we're looking at the source charges, the charges that are going to be generating electric potential, right? Lowercase q would be your test charge. So if I instead of saying point P, if they literally just gave me like, this is another positive charge, and this is 6 times 10 to the negative 9 coulombs, right? Well, I don't care about this one because this is little q, right? This is my test charge. I'm testing the electric field. I'm testing the electric potential at this point, right? I'm not concerned with it because the equation is only concerned with uppercase q, the source charge, what are generating the electric field, right? So it says, look at point P. What is the electric potential at point P? So at point P, I'm looking at everything relative to affecting point P, not including point P itself. Because theoretically, point P, that charge, could be providing its own electric field. That's entirely possible. We're not concerned with the electric field it generates. We're concerned with the electric field it feels, right? So the reason why we use that uppercase Q and lowercase q notation is to differentiate between like what is felt and what is generated, right? Little q is going to be like a test charge. We're testing the electric field. We're testing how that electric field feels at that point. Uppercase q would be the source charge, basically looking at what electric field, what electric potential is generated at that point, right? And so that's kind of the difference there. Now, the reason why there's uppercase q, lowercase q, and whatnot, right? Like, is like with the electrostatic force, you have Q1, Q2. They have to like have an uppercase and lowercase just to denote that there's a test charge and a source charge, right? One that's going to be feeling or reacting to another charge, right? So if you were there earlier in the session, we had a net force like problem earlier where one charge is reacting to another. So if I had two charges like Q1 and Q2 and I want to figure out the force of Q1 on Q2, then I'm looking at how Q2 reacts to Q1. Well, since Q2 is reacting, right? Q2 is reacting. Q2 would kind of be like my lowercase q. Q1 would be my uppercase because that's what's going to be like generating this or causing the movement of Q2. So like if Q1 is positive, Q2 is positive. Q2 is going to be repelled. It's going to move away from Q1, right? So in that case, Q2 would kind of be the lowercase q because it's reacting to Q1. Q1, because it's positive, it's generating an electric field that will repel basically that Q2 away. So generally, long story short, without the derivation of the equation or anything like that, when you see uppercase q, that's your source charge. It's what's generating the electric field and stuff. Lowercase q would be a test charge that's going to be feeling the electric field. So in this case, like I said, if we were to have that point P, if they even gave us a value for that charge, like 6 times 10 to the negative 9 coulombs, we don't give a damn about it, right? Because essentially at that point, it's not I mean, it could be generating an electric field, like I said, but we're not concerned with what it generates. We're concerned with what it's feeling at that point. And so what it's feeling is going to be relative to the other source charges, which are uppercase Q. And yeah, conventionally test charges are positive. Conventionally test charges are positive. Thank Benjamin Franklin for that, because it's like the dumbest thing ever. I mean, like, I don't mean to roast, but obviously, yeah, I mean, it makes sense for them to think that positive charges were carrying, like, or like current was positive charge and whatnot, but like the least they could have done is adjust the convention so like things make sense nowadays, but they still proceed to use the convention, and it's annoying. So anyway, yeah, I guess it's not Benjamin Franklin's fault entirely, but maybe he's just a scientist after him. Anyway, so that's problem 5. Hopefully that makes sense. Problem 6 says, based on the figure below, rank in order from largest to smallest the work required W1, W2, and W3 to bring a test charge of 1 coulomb from a very large distance to points 1, 2, and 3. If they're equal, state so explicitly. So here are the concentric circles. If this will do the shape correctly. I don't know how to... There we go. And... Alright, so there is positive Q in the middle here. This is point 2, this is point 1, this is point 3. When you have a charge like this in the middle and you have these concentric circles around them, what are these called? Like, you don't necessarily have to know them per se to like, well, I guess you kind of do, but yeah, anyone know what these are called? Circles with charges, I suppose. I don't know, someone else. Yeah, Thomas, I see you typing, so. No, not a ring charge. I was saying, like, excellent. So I see, yeah. So I was saying, like, what are these concentric circles called around a charge like this? And they're equipotential lines. They're like regions, right, where the electric potential is going to be equivalent everywhere along that circle. So 0.12 would have the same voltage. If I said 3 here, that would also have the same voltage. If I had signed anything else, any other point along that circle, it's going to have the same voltage or electric potential, right? Now, once again, we know that voltage is equal to KQ over R, right? They have lowercase q here, but they really mean uppercase Q because it's the source charge. It's providing an electric field and electric potential, so just know that. But yeah, so it's asking for the work required to bring a test charge from a very like large distance away to each one of these points. So it's wanting us to rank the energies, right, or the work required to bring that test charge to that very large distance. So for work, right, if you look to your equation sheet, right, I'm trying to find where it's at so I can reference it for you guys, but yep, okay, I see it here. So the work, right, I think it's up in the mechanics section first. Obviously, work is going to be equal to your sum of your kinetic energy plus the potential energy, right? And this is electric potential. Well, if you think about it, is there really a change in kinetic energy? Because if you start off at rest and you move it where it has motion, and then you end it at point 3 or point 2 or point 1, you end at rest as well. So VF is 0, VI is 0. So technically there's no change in the electric or the kinetic energy, right? But there is a change in the electric potential energy, right? And that's because electric potential energy, right, if you remember, electric potential energy equal to K, Q1, Q2 over R, right? let's say if we're moving a test charge, right, like they said. So Q1 and Q2, you have those. You have the central charge and you have the test charge. There's that value. Those aren't changing. What is changing here? When you move it from an infinite distance away to closer to the source charge, what is changing here in that equation? R, right? So if I am at an infinite distance away, R is infinite. What is U? If R is infinity, what is U? 0, right? So I effectively have no potential energy far away. So the closer I get, the larger potential energy I have, essentially. And so when I'm looking at this, right, there's also another equation which tells me U, my electric potential energy, is equal to my test charge times the change in the voltage, right? My test charge times the change in my voltage, right? Test charge isn't going to change once again, but my voltage might. My voltage is equal to K times the source charge divided by R, right? So if I just adjust this to be uppercase Q, which it should be, if I increase my distance away from my source charge, what happens to my voltage? So if I go outwards like this, what happens to the voltage? Decreases, right? So if this was 30 volts, this might be 20, and this might be 10 then, right? Those concentric circles, right? So as I move away, I decrease in my electric potential. And it makes sense in the context of this equation right here. So if you decrease your electric potential, eventually to a point where you have infinite distance away, V would be 0, right? And so your electric potential energy would be 0 as well. Now, 1 and 2, because they are on the same circle, they're the exact same radius away, they would have the same potential. So that makes that circle an equipotential surface or an equipotential line, right? Now, we already kind of see here that the electric potential is going to decrease with distance away from the source charge. We went from 30 to 20 to 10, right? Well, if the initial point is 0 volts, and you're getting it to 10 or you're getting it to 20, right? Which one is going to have the greatest change in voltage? Moving from this initial point to what circle is going to have the greatest change in voltage? Exactly. Because you move from 0 to 10 volts, which is at 3. I'm just making up numbers, by the way, just so you guys can see this. 0 to 10 volts, that's an increase in 10 volts. But from 0 to 20 volts, that's an increase in 20 volts, right? So the closer you get to the circle, to the source charge, the greater the voltage change is going to be, right? Because it's basically like, oh, I went from like experiencing no effect from any charge ever to getting ever closer to this charge. So the closer I get, the greater the electric potential change is. And so if this is increased, right, if that change in voltage, like instead of being 0 to 10, it goes 0 to 20, right, and my test charge is the same, then my electric potential energy is going to increase as well. So once again, since we said that 1 and 2 have the same radius, they have the same voltage, then 1 and 2, U1 would have the same potential energy as U2. And they would be greater than the potential energy of U3. Why? Because if the voltage from 0 to 10 is just 10, and from 0 to 20 is just 20, then if we were to plug that into the equation here and just kind of look at things conceptually, we see that the change in voltage from infinite distance to 3 is going to be less than the change in voltage from the infinite distance to 2 and 1, right? And 1 and 2 will have the same voltage change because they're the same radius away, right? So the energy to get from infinity to 1 and 2 would be the same, and that would be greater than the energy to get from infinity to 3. And so once again, if the only work being done would cause a change in the potential energy, then this can be amended to work 1 is equal to work 2, and that's greater than work 3. Does that make sense? Sound good? So that's problem 6, right? Problem 7, kind of long. So problem 7 is electric field. It says a charge Q1 is equal to negative 2.5 microcoulombs, and it's placed to the right of point A. They had point A, and you have Q1 over here, right? And it's a negative charge. Give both the magnitude and direction of the electric field at point A due to this charge, right? So they just say point A, right? Theoretically, point A could be a negative charge, right? Could be a positive charge. Doesn't matter to us. Doesn't matter what charge it is. Part A is concerned with the direction of the electric field at point A due to that charge, due to charge Q1, right? Electric field lines will point in the direction, by convention, of how a positive test charge would react to it. So, if I had a negative charge and I had a positive test charge, little q, the electric field line would point inwards towards Q1, or to the right here, right? Because that's how a positive charge would move in response to a negative charge, right? Now, that is going to be the scenario that you're going to probably see with all these problems, that they're going to give you a point and they're going to ask you for the electric field line, direction, magnitude, all of that. And they just say point. You're assuming that we're going by the convention and that the electric field line should point as if there was a positive test charge there. So this would point directly to the right. And then they're asking us for the magnitude, right? So we know that electric field, there's an equation for it. We can use it. Where is it on the equation sheet? It's point charge, so it's under electric field, and it's electric field of a point charge. So it's K times the absolute value of the source charge divided by R squared, right? So it's again 9 times 10 to the 9th, and then multiplied by your source charge, which is 2.5 times 10 to the negative 6. Remember, it was negative, but we had to make it positive because it's magnitude, and then divided by the R squared. And the R in this case is 5 centimeters, or 0.05 meters, and then we have to square that, right? And then you figure out what the electric field would be at that point, right? I believe that's 9 times 10 to the 6 newtons per coulomb, right? So that's part A. Part B is saying a second charge. Yeah, I made it positive again because it's the magnitude or the absolute value. Because that's if you look at the equation of the point charge or the electric field of a point charge, it's K times the absolute value of the source charge divided by R squared. Yep. So that's that for part A. For part B, they're saying, okay, well, what if we assigned a second charge, right? A second charge where it was, this is point A. Here's Q1 that's negative. Here's Q2 that's positive now, right? That charge was 9 microcoulombs, that Q2. And so it says it's placed as indicated, calculate the magnitude and direction, angle with the x-axis of the electric field at point A, due to Q2 only, right? So we're only concerned with Q2 at this moment, the magnitude and direction of the electric field of Q2, right? So once again, assuming that this is going by convention for electric field lines, then how would the electric field line point at point A? What would it look like? Would it be to the right relative to Q2? Like, would Q2 result in an electric field that points to the right, points to the left, this way, that way, downwards? What? How would the electric field lines be drawn? And this is, yeah, at point A. So it would be pointing away, not towards, right? Because remember, the convention is that it's a positive test charge reacting to the source charge. So if we were to draw electric field lines just from Q2, it would kind of look like this. Everything is outwards, right? So if we simply just like look at, what if we had a line that was along point A? That's how the electric field would look like. You see what I mean? So the electric field line. Go ahead. No, go ahead. It's fine. It's fine. Go ahead. Yeah, so they'll tell you just point A, and you assume that we're going by the convention that the electric field lines should be pointing in the direction of how a positive test charge would react relative to the charges. So that's always like, yeah. Yeah, no, I was saying like, I mean, at that point, like, um, for a positive source charge, electric field lines would be pointing outwards, and for a negative source charge, they would be pointing inwards towards the charge. But yeah. Yeah, I think so. Yeah. Yep. And so essentially, yeah, basically, if we assume, like, based on the convention, if this were to be a positive charge, then it would be repelled by that source charge. It would move. And when we're dealing with this for electric fields, like, we're looking at the direct distance or the direct, like, axis between these two charges. So this, like, we're not looking at x and y components for it, right? We're just looking at the direct axis, the direct connection between them. And so electric field line would be pointing this way along point A. And so they want us to calculate magnitude and direction of the electric field at point A due to Q2 only. So E2 be equal to K times the absolute value of that Q2 divided by R squared, right? And so if you simply just take your 9 times 10 to the 9th, multiply it by your Q2, that was 9 times 10 to the negative 6 coulombs, and divided by your R squared, well, what's your R squared here? They told you that the distance between Q2 and A is 6 centimeters, right? And the vertical distance was 3 centimeters, right? How can I figure out the direct distance along that axis, right? Yes, exactly. In that case, we do use x and y components just to get our r, right? So we use Pythagorean theorem. 3 squared plus 6 squared will give us like, I kind of skipped forward. I did it in meters because it has to be in meters for SI units. So 0.03 squared plus 0.06 squared will give us like 0.067, or once we take the square root of that, 0.067. So this distance here is like 0.0, I did 2 points, I got 0.067 meters, right? And so that's your radius, 0.067 meters, and then we square that, and then that's our electric field. Excellent. But what about our angle? How can we figure out the angle here? Because this is the angle, effectively. That's our theta here. Exactly. Inverse tangent. So inverse tangent of 3 over 6 will get us around 26 degrees. So we can say, whatever that electric field is, it was like 1.8 times 10 to the 7th, I think. And then at an angle of 26 degrees. You don't have to say like, what is it? North of east or anything like that. You can just say 26 degrees. That's it. Because it says angle with the x-axis anyway. So you can just throw in your degrees and that's it. That's B, right? For C, they're asking for the x and y components of the electric field due to Q2. So this is just using the angle that we used before. That's pretty simple. Q2x would just be equal to Q2 cosine theta, Q2y, Q2 sine theta, right? Because if we take cosine, right, which is adjacent over hypotenuse, so adjacent over hypotenuse, that gives us the x component. Sine, which is opposite over hypotenuse, will give us the y component, right? And so we just take Q2, that 1.8 times 10 to the 7th, times cosine 26 degrees. Make sure you're in degrees, not radians. That would give you the electric field due to Q2. Same thing for Q2y. If you do Q2 sine theta, you should be able to get your net, or your Q2y, your y component of Q2. Does that make sense? But yeah. For part D, it says give both the magnitude and direction, angle with the x-axis, of the net electric field at point A, right? Well, at point A, we're dealing with Q1 and Q2 now. The previous two parts were only asking us to deal with Q2. Now we're asking to deal with the entire net electric field from Q1 and Q2. Does Q1 relative to point A really have, like, that electric field? Does that have a y component really? So if you think about it, right? No, exactly, right? So remember we had it where it was pointing directly to the right. So there's no really y component of the electric field generated by Q1. So E net y would simply be equal to just Q2y, right? But E net x is equal to Q2x plus Q1x, right? And we already kind of had Q1 before, right? Q1x before. That was the 9 times 10 to the 6th from before, right, in part A. So this is just a matter of adding up the x component of Q2's electric field and Q1's electric field. And Q1's electric field just so happens to be only in the x-axis direction. So if you just add those two up, you should be able to get your net x, right? Once again, now that we're trying to find the net electric field, we have to take into account both the net x and the net y components, right? So we know that E net via Pythagorean theorem would just be equal to E net x squared plus E net y squared, right? And so if you take, well, in that case, with the square root, it should just be E net like that. So if you do Pythagorean theorem, you plug in your E net x, square it, plus E net y, and square it, and then take the square root of everything. That should give you your E net. Right? And so that's our net electric field. Once again, if we want to figure out the direction now, we can do like some trig identity stuff, right? So we have our y, our net y, and we have our net x value. Net y for this was like 7.8 times 10 to the 6th, and net x was 2.5 times 10 to the 7th, I believe. So both of these we can see here, even just by drawing what's going on, that it's pointing to the right and upwards like that, right? So we have a y component and an x component. If we were to take the inverse tangent of the y component over the x component, then we could get the angle, right? So if we wanted the angle, it would be inverse tangent of E net y over E net x, right? Because at that point, once again, you're taking that opposite over adjacent, taking the E net y over E net x, y component over x component, and then that should be able to get you your angle. And I believe the angle in this case was 17 degrees, roughly. But yeah, does that make sense for problem 7? Okay. Problem 8. Is saying an electron is brought in from far away towards a point charge of negative 4.5 nanocoulombs. Interesting. So it says part A. What is the electric potential energy of the system when the electron is at a distance of 2.8 millimeters from the point charge? What is the electric potential energy, right? Electric potential energy, it's just a matter of using the equation for it. We know that it's K Q1 Q2 over R, right? R is the distance between the electron and the point charge. Well, K Q1 Q2 over R, right? We know that's 9 times 10 to the 9th. Q1, we can say that that's our point charge, which is negative 4.5 times 10 to the negative 9. And then Q2 is the charge of the electron, right? And charge of electron is given to you at the very beginning of the formula sheet, and that is 1.6 times 10 to the negative 19 coulombs. You just divide by your radius at that point. And the distance, which is your radius, is that 2.8 millimeters. And that's the same as 0.0028 meters. And that should give you your potential energy at that point, which is like 2.3 times 10 to the negative 15 joules, I believe. Oops. Should be a negative for both of them because the charge of the electron obviously is negative, right? So keep that in mind. Because 1.6 times 10 to the negative 19 coulombs is the charge of both an electron and a proton. But one's negative, one's positive, basically. And so you have to add in the extra negative sign to get a positive potential energy there. Because also think about it, like the way I like to think about things for electric potential energy is that if you're moving a charge towards a quote unquote uncomfortable position, then you're increasing its electric potential energy. So I'm moving an electron, a negatively charged particle, towards another negatively charged particle, right? That's uncomfortable for it. It does not want to go near another like charge. So making charges, quote unquote, more uncomfortable, getting them to positions where they would normally repel, increases their electrical potential energy. Getting them to positions where they are more comfortable, right, where they are either away from each other if they're like charges or towards opposite charges, that makes them more comfortable. They have less potential energy. And the reason why I'm saying like comfortable and not comfortable and stuff like that is that like if they're in an uncomfortable position where they have like two negative charges next to each other, they're very uncomfortable, they have high potential to move, high electric potential energy, right? So they have high potential to move. So if you gave them the opportunity, they're going to move away from each other. So that electric potential energy that's built up is going to get converted into kinetic because they're just going to fly away from each other. As opposed to if you have opposite charges, they'll attract each other. They'll be very comfortable. They won't want to move. They'll have very low potential energy. They have low incentive, low potential to move. So, at that point, they're very comfortable, like I said. So I think that's a nice way to think about things as well, is that moving two like charges together, yeah, I can draw it out to be able to better visualize it. Absolutely. Thank you for letting me know. So if you have two like charges really close to each other, high electric potential energy, right? Very uncomfortable. They have a lot of potential Potential both meaning as like electric potential energy and like, you know, in the analogy that I'm using, like actual potential to like move, right? A lot of potential to move, basically. Because you have a lot of electric potential energy that can all get converted into kinetic, right? They want to move away from each other. Want to move away. Now if you have, and they will go this way and go that way, they will go flying, right? But if you have positive charge and a negative charge, they're very comfortable. They want to stay, right? So this is low electrical potential energy. These are very comfortable, right? Low potential to move. So in this case, like we have two negative charges. And so those would be like charges that would be near each other, very high potential energy because they're very uncomfortable. They would have a lot of potential to move away from each other. That's the idea there. Now, like, what was I going to say? There's also this concept of just electric potential alone, not just electric potential energy, but electrical potential, right? And that's your voltage, that's your V, right? So the convention is that for electric potential, if you have like two plates here, they have positive charges, negative charges, right? They tell you in the reading that positive charges have high potential, negative charges have low potential, right? That's what they tell you in the reading. Now, basically to like keep up with that convention, right? They're referring to things in terms of, once again, positive test charges. So if I have a positive test charge here next to a positive, like charged plate, right? It's in a very uncomfortable position. It's going to want to move away from that positive plate, right? So if it's very uncomfortable, it has a lot of potential, high potential energy to move, right? And so if you look at the equation of the electrical potential energy relating to voltage, right? U equals Q delta V. Well, the voltage would be very high if the electric potential energy is very high, right? So if this is very high, and we have a specific test charge that we're looking at, right? Then in order for that electric potential energy to be very high, you have to have a very high electric potential, right? A very high voltage at that point. So they come up with this convention that positive is high potential and negative is low potential because they tested it out with a positive test charge and they figured out, okay, well, these things are in a very uncomfortable position. They have a high potential energy, therefore they must have a high potential, electric potential, right? So this high potential energy, very uncomfortable, means also high potential, high electrical potential, V. And this is U, right? And so if you let this test charge go, it's going to want to move to a more comfortable position, which is the negative charge, right? So if I think about this, what do I want to say? So you have a very high potential to move at this initial point. Let's say you might have like 30 joules that you're working with, right? 30 joules that you're working with. This is the high potential energy. Let's say those 30 joules will get converted into kinetic energy, the charge moves, and now you end up with like 0 joules of potential, right? If we rearrange this equation, we can also say that voltage is equal to the energy per unit charge, right? So we went from 30 joules, very high potential energy at the beginning, at the top, in a very uncomfortable position, to a very comfortable position, low potential energy, low incentive, low potential to move, right? So we went from 30 joules to 0 joules. Let's say our Q, our test charge, has a charge of 1 coulomb, right? You went then from, so we said this is 30 joules over 1 coulomb, you went from an area that has 30 volts to an area that has 0 volts, right? So you just decreased your electric potential, your voltage. You went from 30 volts to 0 volts, right? So delta V is negative. So positive charges move from an area of high potential to an area of low potential. And so because they tested things out with positive charges, the convention sticks. High potential is positive, low potential is negative, right? Well, in reality, like I said, things are negative charges that are moving. So if I were to assign a negative charge here, right? If I were to think about things in a negative charge, well, what if I had a negative charge down here? Actually, you know what? Let me just keep this. If I had another set of plates, positive, 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 negative, 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 negative. If I had a negative charge right here, it also has a high electrical potential energy because it's in a very uncomfortable position. It wants to move away from those negative charges. It wants to get to a more comfortable position where it's attracted to the positive charges. So this is high U, high electrical potential energy, right? And then based on that convention, well, we already said that negative charges would have low potential. So this is low V, low electrical potential. At this point, this would have a low U because you're in a very comfortable position now, but it would have a high V because this would be high electric potential based on the convention, right? So positive charges move from an area of high potential. So positive charges move from high potential to low potential. And that's high electric potential to low electric potential, like high V to low V. And negative charges will move from low potential, low V, based on the convention, to high V, based on the convention, right? What's common in both of these scenarios is that both of these charges, whether positive or negative, will move in a way that lowers their electrical potential energy. They always want to move to a more comfortable position. That's what's constant between them. Now, really, in my opinion, the way they should have amended, like, the definition of electric potential is that electric potential, because V equals U over Q, it's dependent on that electrical potential energy. It should essentially kind of be like a measurement of comfortability, right? So just how comfortable the charge is, essentially, right? So if I'm going by convention, negative charges would move from low potential to high potential because negative charges, right, would move away from other negative charges, which have low potential, towards positive charges, which have high potential, based on that convention that we discovered here, because we went from 30 volts to 0 volts, where 0 volts is less than 30. So negative charges have lower potential, positive charges have higher potential. That's the convention. But in reality, you can kind of think about things as like potential being a measurement of like how comfortable the charge is. So this is just kind of for your own understanding, but like for electric potential, negative charges next to other negative charges would be very uncomfortable, have a high electric potential in that sense, and they would move towards low potential to the positive. And the reason why I'm saying this and why it like might seem confusing is that if you think about it, right? If we did that 30 and 0 thing again, where V is equal to U over Q, right? V equals U over Q. If this was 30 joules, but now we have or this is 0 joules, my bad, because this is the point where there's very comfortable position, so 0 joules of energy there. That's not actually the case, I'm just giving an example. And this charge would be -1, right? This is 0 once again. But here, V equals U over Q, we have 30 joules, very uncomfortable position, high potential to move, but a -Q. So this is -30. So we went from -30 to 0. Once again, we see that positive has high potential, negative has low potential. But you see that the change in the voltage is now positive. 0 minus -30 is equal to 30 volts, while the change in potential here was 0 minus 30, and that's negative 30, right? So I think the book had said, like, all charges move from high potential to low potential, right? But in this case, you can see, like, what's going on is that it's kind of the opposite. But when I'm talking about, like, comfortable and being uncomfortable and stuff, that's just kind of help you better understand, like, what's going on. And so the reason why you see this, like, increase in the voltage, right, is that it's like I went from, like, a very uncomfortable position to a more comfortable one. And so I should see that increase in the potential. But just to simplify things down, and that's how you're going to solve things in the exam and stuff, and that's what's going to be referenced, just stick with the conventions. The convention is that we're always looking at things with positive test charges. There have been examples that I've seen that would use a negative charge, right? But you can just look at things as, okay, positive charges will move from an area of high potential to low potential. Negative charges will move from an area of low potential to high potential, where high potential is positive, low potential is negative. Does that make sense? We all good? Just like that idea of electric potential and electric potential energy, the relationship between the two? Do you guys have any questions? Okay. So B asks, what is the work required to bring the electron from 2.8 millimeters to a smaller distance of 0.7 millimeters from the point charge? So essentially, like we said earlier, we kind of define things with work equal to the change in the electric potential energy, right? Because you start off at rest and you end up at rest, so there's no change in the kinetic really at that point. So our work is only going to be made up of changes in electric potential energy. So we're essentially just looking for UF minus UI, right? So the difference between the final electric potential energy and the initial electric potential energy. So you're bringing the electron from 2.8 millimeters to a smaller distance of 0.7 millimeters. So your final position is going to be at that 0.7 millimeters, right? So this is KQ1, Q2 over that new distance, and then minus that original potential energy that you had, which was at 2.8 millimeters, right? So that was like 2.3 times 10 to the negative 15 joules. I think that's what it was. Yeah. So Q1 and Q2 are going to be the same. Still that charge of the point charge and still the charge of the electron, right? Just make sure you have those both negative, right? Because the electron is negative and the point charge is negative as well. And then, yeah, so if you set this up as 9 times 10 to the 9th, and then multiplied by negative 4.5 times 10 to the negative 9, and then negative 1.6 times 10 to the negative 19, divided by 0.0007. Right? Yeah, so the final potential energy, they said we're bringing the electron from 2.8 millimeters, right? So remember in the part A, they were saying that the electron is at 2.8 millimeters. So initially, it's 2.8 millimeters. So that's the UEI. Let me add just E here and E there. And then the final electric potential energy is that at that distance of 0.7 millimeters, right? So we know that the electric potential energy is equal to K, Q1, Q2 over R, right? So Q1 is going to be that point charge. Q2 will be the charge of the electron, right? K is your 9 times 10 to the 9th, and your R is going to be the distance from the point charge, that new distance away, which is that 0.7 millimeters, right? That's the final distance away that it is. Because it's like you brought it from 0.28 millimeters away. Here's the point charge, and here's the electron, right? You brought it from 0.28 millimeters away to 0.7 millimeters away. So this is your initial, this is your final, right? And so you just plug in your new radius, basically. Does that make sense? And then if you carry out that like expression here, you should see that the work ends up being like 6.9 times 10 to the negative 15 joules, and that's positive work that's being done, right? And the reason why it's positive work, right, we're seeing an increase in electrical potential energy. Why are we seeing an increase in electrical potential energy? Why is the work positive? Because we're making these charges more uncomfortable, right? You're bringing two like charges closer together. You're making them more uncomfortable. You're increasing the electrical potential energy. They have more potential to move. They have more incentive to move. Does that make sense? Okay. Awesome. Part C, it says the electron is then released from this position, from a position of 0.7 millimeters from the point charge. And it's asking what is the final speed of the electron when it's far away from the point charge, right? So this is just saying like, okay, it's kind of what I was saying earlier, right? So if we were to just let these charges go, they have a lot of potential built up. They have a lot of potential to move. What if we let them go? What happens, right? So in general, if you have potential energy built up, right? Let's say maybe for like gravitational potential energy, if you're on top of a cliff, right, or at the top of a cliff, and you have a certain height, you have certain gravitational potential energy. Once you start falling, what happens to the gravitational potential energy? Once you start falling like off a cliff, what happens to your gravitational potential energy? Exactly. So if I'm in this very uncomfortable position and I'm let go and I'm allowed to seek out a more comfortable position, what should happen to my electrical potential energy? Exactly, right? So that decrease of energy can't just be lost, right? Where does that energy go to? Kinetic, right? So whatever decrease that we see in our electrical potential energy, we should see a corresponding increase in the kinetic energy, right? So you can say like EI equals EF, right? UI plus KI equals UF plus KF. We want to figure out the combination of the initial and final energies, right? So initially, we have some like electrical potential energy, which is near that point charge. This UI is going to be equal to the electrical potential energy at that 0.7 millimeter point, right? So it's just this part. The electrical potential energy at 7 millimeters. That's our UI. Ki would be 0 because we haven't started moving yet. Final energy, there would be 0 electrical potential energy because it says far away. So whenever they say far away in these contexts, we're assuming that it moves an infinite distance away. And if infinite distance, since K(Q1, Q2 over R is equal to electrical potential energy, that R, if it's made infinity, if it's made super far away, then something over infinity is going to be equal to 0, right? So your electrical potential energy far away would be 0, but you have some final kinetic amount, right, that you moved away with. So it's basically saying like we have this built up energy, this built up potential to move, and we want to convert all that potential to move into actual movement, right? So we want to deplete all our electrical potential energy and convert it entirely into kinetic. So your final electrical potential energy should be 0, and you should have some final kinetic instead. So U, EI, our electrical potential energy initial, should equal our final kinetic energy. So this is that electrical potential energy at that 7 millimeter point, and that's equal to half mvf squared. You might be thinking, well, how the heck am I supposed to figure out m? What particle are we dealing with here that's moving? An electron. And we have the value of the mass of the electron here in our equation sheet, and that's 9.11 times 10 to the negative 31, right? So 1/2 times 9.11 times 10 to the negative 31 kilograms, right? And then VF squared, and that's equal to our UEI. And our UEI, our electrical potential energy initial, that, I don't have a value, or do I have a value? Yeah, I do have it. No, I don't. Never mind. I don't have value calculated out for it. But it's whatever you get for that expression right there, just this part right here. The 7 millimeter part only. But yeah, once you get that, you can figure out your final speed. You got 9,200. Oh, I don't think I got that. Let's see here. So this should be, let me write it out. So this should be 9 times 10 to the 9th times negative 1.6 times 10 to the negative 19 coulombs times negative 4.5 times 10 to the negative 9 coulombs. Remember, you have both negatives that you have to include because it's a negative point charge and a negative electron, obviously. And then this radius should be 0.0007 meters. And this is equal to 1/2 times 9.11 times 10 to the negative 31. Oops. And then this is VF and squared. Yeah, I think you should be able to get, the final answer I got was like 1.4 times 10 to the 8th meters per second. Oh, you meant that for your value of KF, then yeah, if you, your value of KF would be the same as your electrical potential energy, but yeah. I don't know what that value would be, to be honest. I haven't calculated it out. Make sense? Well, I cannot write today. Any questions about problem 8? Nope. All right, fair enough. Problem 9. So problem 9, capacitance, right? So now we can get into some of this capacitance stuff. So with your circuits, like whether you have resistors or capacitors, if you know one, you know the other. Resistors are, like, whatever you do for resistors is the opposite of what you do for capacitors. And whatever you do for capacitors is the opposite of what you do for resistors, right? They're kind of inverses for each other. So to sum things up off the top of my head, just so I can, I'll double check. Let me pull up the equation sheet just so I can double check that I didn't screw this up. And this is what's really nice about the equation sheets for 132 is that they actually have like concepts down. So like I think midway through the exam I forgot how to, like, if I should like add up voltages or if I should keep the voltage the same for like parallel resistors or something. And it was like right in front of me on the what's it called, on the equation sheet, telling you like how to calculate parallel, like how to find the equivalent resistance for parallel resistors or something like that. So for resistors, if in series, right, then you add up voltages. Simple as that, right? You add up voltages for resistors in series. With resistors in series, you also simply add up resistors. So your equivalent resistance, Rs, for series, would just be equal to the R1 plus R2 plus R3, whatever, how many resistors are there in series, right? So your voltages, you'd add them up, different voltage drops, you just add them up to get the total voltage drops for series ones, right? And for your resistors, you add up the resistors simply. But if you're in parallel, voltage is the same across every single resistor in parallel. And for your resistors in parallel, you do not directly add them up. Rather, you add up their reciprocals. So 1 over your equivalent parallel resistance. And equivalent resistance is basically taking all the resistors in a, or not all of the resistors, but a specific set of resistors and combining them together in some way to get like a pseudo resistor that would have like the combined resistance of all of them together, right? So 1 over the equivalent parallel resistance is equal to 1 over resistance 1 plus resistance 2 plus resistance 3 and however many like things you have, like resistors you have in that branch, right? Remember, because all these are branched together like I was explaining earlier. So if I have a resistor that's like, so these are my branches here again, right? Resistor here, resistor there, resistor there. R1, R2, R3, right? I can't just do R1 plus R2 plus R3. I have to do 1 over R1 plus 1 over R2 plus 1 over R3, right? Let's say all of these are equal to 2 ohms. So 1 over 2 plus 1 over 2 plus 1 over 2, right? So that's 1.5, right? But that's not your equivalent parallel resistance. 1 over your equivalent parallel resistance is equal to 1.5. So 1 over 1.5 is equal to your equivalent parallel resistance. Keep that in mind. Do not make that mistake. So once you add these up, once you add the reciprocals, that's not the end of your answer. You take the reciprocal of that to find out your equivalent parallel resistance, right? Does that make sense for resistors, parallel ones, series ones? And I can draw it up here too, like if you have this branch, right, you have this battery here. We have branch, resistor there, resistor here. Does someone have a question? Did I? I think you might be looking at capacitors. You're good. Yeah, so like that's what I'm saying. Like whatever you do for one, you do the exact opposite for the other. So if you know resistors really well, you can just figure out capacitors by doing literally everything opposite to the things that you've already done. So for capacitors, right? I can literally just like copy all of this. Right, let me grab this, put it over here. So capacitors in series would have, what's it called? So for their voltages, do the voltages add up? I'm trying to remember. Yes, I think so. Let me double check, just so I'm not messing anything up. Yep. You add up the voltages if they're in series for capacitors, but for capacitors in series, right? For capacitors in series, you do not simply add them up, you add up reciprocals. Right? Did I say that up here? Add reciprocals. So capacitors in series would add up reciprocals. So 1 over the effective capacitance in series would be 1 over C1 plus 1 over C2 plus 1 over C3, etc. Right? If they're in parallel, the voltage should be the same across every single capacitor in parallel. But then your capacitance can be added up very simply. So capacitance, not in series, in parallel should just be equal to C1 plus C2 plus C3, and that's it. It's very, very simple, right? For capacitors in series, there's also this concept of charge, right? For capacitors in series, charge has to be the same. Charge has to be the same across all of them. And here, charge has to be added up. The charge between all the branches, the branched capacitors in parallel, will have to add up. Similar thing here with current. Current has to be the same for resistors in series, and it has to add up among the branches in parallel, right? The idea is that, like I said earlier, like if I had 6 amps going through here from the battery, 6 amps goes through this first resistor, that's fine. I come in with 6 amps, I come out with 6 amps. I come to this branch, right? 6 amps goes in, 6 amps must come out, but they split off. Some of the current can go here, some of the current can go there. Maybe 4 amps here, 2 amps there, right? So the 4 and that 2, they have to add up together. The current has to add up among resistors in parallel. But then once I get to 6 amps outside here again, move through this last resistor to the left, still 6 amps. So resistors in series, current has to be the same. Capacitors in series, charge has to be the same. And remember, current is a measurement of charge per unit time. So that's why series for both of them, charge, the current has to be maintained in series. But for parallel, since the current will split up into different branches, the current, like the distributed currents, have to add up to each other so that the input has to equal the output, right? For this branch, like if I'm just drawing like a circuit here once again, right? If I were to try to figure out the equivalent resistance of everything, well, if I erase some of these values here, let's say this is 2 ohms, this is 3 ohm resistor, this is a 5 ohm one, this is a 5 ohm one, right? So how would I go about simplifying this circuit down a little bit? I might as well actually just like kind of go through it because I know you guys had some trouble with this one. So the way I do it is like I start from the battery and I follow through. I go through here, I'm like, oh, awesome, resistor, cool, we're continuing. Oh, I see a branch. Shoot. I need to simplify this branch first. Well, this branch means that there's in parallel resistors. So parallel resistors, 1 over 5 plus 1 over 5, because resistors in parallel. You have to add up the resistors like that. So 1 over R1 plus 1 over R2, 1 over 5 plus 1 over 5 is equal to 2 over 5, which is 1 over RP, right? So our equivalent parallel resistance would actually be 5 over 2, which is 2.5, right? So this becomes a very simplified pseudo resistor here that is now in series with the rest, right? The idea is to get everything in series. So now I'm at 2.5 ohms for this pseudo combined resistor here, right? I go back to the battery. Every time I simplify, I start back at the battery, just so I can follow through again. So I'm at the battery, 2 ohms, 2.5 ohms, oh cool. Now we go back, do I see another branch anywhere? No, 3 ohms, cool. Go back, okay, I've reached the negative terminal of the battery, awesome. Now I have everything in series. If everything is in series, you just add up the resistors. So I can add up the 3, the 2.5, and the 2 to make one huge combined pseudo resistor, right? 2.5 plus 2 plus 3, that gives me a overall combined pseudo resistor that is 7.5 ohms, right? Boom. That's it. That's my simplified circuit, right? So you travel through, trace the line, trace the wire. If you encounter, like the idea is to get everything in series. If I encounter a circuit in series, no branch point between the current, like in the wire or anything like that, awesome, continue on, right? As soon as I see a branch point, I try to simplify it down. Simplify it down, got it back in series, I start back at the battery. From the battery, go through the first resistor again, through the simplified second resistor, awesome. Do I see another branch point? Cool, I will simplify it now, right? Then I go back to the battery. I go back up again. All right, got to that simplified pseudo resistor again. Cool. Any other branch points? No. Everything's in series. Add them up all together, and then that's your simplified circuit. So the goal is to get everything finally in series, right? To avoid any branch points, right? So that being said, that's how you can do stuff for resistors in series and parallel. Like I said, capacitors would be the same thing, except everything's kind of the opposite. Same concept with the whole branching point thing, same concept with the like simplifying everything down to a pseudo resistor. Now, what if I had a branch point here that was like, it was like this? All right, so I have this branch, I have resistor here, resistor there. What if I have another resistor here? So I have current coming through here, right? Current goes in, gets split here, gets split there, right? Well, as the current travels through here, through this R1 and this R2, is there a branch point? Does the current split off additionally between R1 and R2? I'm asking you guys, by the way. Is there any branching off between R1 and R2? Do I see any additional branching off? No, right? So they're connected consecutively, right? You can think of like resistors in series, like a TV series is consecutive, right? The episodes are consecutive. They follow each other in a chronological order. There's no branching off. There's no like weird like tangents between episodes and stuff, right? Everything seems to kind of be in a chronological order. There's no redistribution of the current. Everything is consecutive between R1 and R2. No additional branching off points, right? Man. So that being said, R1 and R2 would be in series, right? So you can add up R1 and R2. So those would be they would make up their own pseudo combined circuit here called R12. And this would be R3, for example, right? Now R12 and R3 are fully in parallel with each other, right? That combined resistor and that other resistor are in parallel now. And then you just find the parallel equivalent resistance. So you can combine this down to a resistor that would be in the series. It would be in series with everything else. And so you just be left with this resistor called R123. This combined pseudo resistor here, this equivalent resistor. Like I said, same deal with capacitors and stuff. And we'll see that here in a second. So with part A, right, for problem 9, says two capacitors of capacitance C1 equals C2 equals 4 microfarads are connected as pictured, right? The connection here is you have a battery and it's 12 volts, right? You have a capacitor C2 here, right? And C1 there, and we know that C1 equals C2. So it says determine the total amount of energy stored by the capacitors, right? So we know that we can relate energy to capacitance via a number of equations, and you can find them under the capacitors section on the formula sheet, which is U is equal to half CV squared, right? So 1/2 CV squared. We know our voltage. How about our capacitance? Well, this equation factors in the capacitance of the entire circuit, right? How can we simplify this down real quick? For capacitors in are these in parallel or are these in series? Parallel, right? So if I were to trace this, I come to a branching point, right? I could either go through C2 and then continue the circuit this way, or I could go through C1, right? There's this branching point, there's distribution of current, there's distribution of charge here, right? So they're connected in parallel. I can find capacitance in parallel by just simply adding up capacitors in parallel. We'll just simply add up C1 plus C2, right? So 4 plus 4 would be 8 microfarads, right? So half times the capacitance, this is 8 times 10 to the negative 6 farads because it's microfarads. We want it to be in SI units. And then voltage is just 12 volts. And then we square that, and that's our energy, right? For part B, this is what I was talking about, where it says, without unplugging the battery, a dielectric of kappa equals 2 is used to fill the space between the plates of the third capacitor. I think they meant the second capacitor here. What would be the new total energy stored by the capacitors, right? So we know that for a capacitor, if it has a dielectric substance inserted in between it, how can we figure out the new capacitance? Exactly. So C new, right, or C2 new is equal to K, right, our kappa dielectric constant, times C2 old. So that's 2 times the old C2, which is 4 microfarads, and that's 8, right? And now we add 8 plus 4, right? So C2 new plus C1, oops, and that's equal to 12 microfarads, right? And now it's asking for the new total energy. So U is equal to half CV squared, right? So 1/2 times 12 times 10 to the negative 6, and then times 12 volts squared again. Reason why we add them up again is because we're wanting to figure out the new total energy. To figure out the new total energy, we have to have the total capacitance. How do we find the total capacitance? We simplify the circuit down. How do we simplify the circuit down? Okay, let's look at tracing the current. We go from positive terminal here. Okay, we see a branch point. Let's simplify this down. Let's simplify down this branch point, right? So this is in parallel. So we add up capacitors in parallel, simply C1 plus C2. That's why we do 8 plus 4, that's 12. And then we can figure out the rest, right? For C, we're saying determine the amount of charge in each capacitor in the previous setup, right? So remember what I said earlier here. Capacitors in series, the charge has to be the same, but capacitors in parallel, the charge has to be added up, right? The charge has to be added up for capacitors in parallel, right? Because effectively the charge or the current gets split up between them, right, at that branch point, right? So we have maybe 7 coulombs coming in. 5 might go up to the top, 2 might go down here, but when they reunite at this output point to come back to the battery, they have to be a unified 7 coulombs again, right? Or 7 amps or whatever, right? And so the charge has to add up between them, right? So we see here that there is a relationship between the charge and the capacitance and the voltage, right? So Q equals CV is what we're looking for, right? That can help us figure out the charge in each capacitor. Well, we have a capacitor with a dielectric, we have a capacitor without a dielectric, right? And so capacitor with the dielectric is that C2, right? So Q equals C2V. That was Q2. And C2 was that 8 microfarads, right? So that's 8 times 10 to the negative 6 farads times 12 volts. And remember, for capacitors in parallel, voltage is the same across every single capacitor in parallel, right? That's pretty easy. So we can just do the capacitance times the voltage, and we get that. We can do the same for Q1. C1 times V, right? First capacitance was 4 times 10 to the negative 6 farads, or 4 microfarads, right? And then times 12 volts. And then boom, we got Q1 and Q2, the charge across each capacitor, right? Now, for part D is where things get interesting. So it says a third capacitor with charge, or the capacitance 4 microfarads, is added as depicted. So it's added in a way like this here. So we added another capacitor here. So once again, if I trace my current, here's my branch point, right? Some charge can get split between this branch and this branch, right? Okay, awesome. Cool. Let me follow the branches real quick. So if I were to follow the current along here, follow the current along here, I meet C1. Oh, but I meet C3 as well. Between C1 and C3, is there any additional branch point? Between C1 and C3? No, right? So I go from C1 to C3, the current does not get split up anymore, right? There's no additional splitting up between C1 and C3. So what does that mean for C1 and C3? In series, right? They're connected consecutively to each other, right? And so we could combine them to make like this pseudo combined capacitor, right? So what do we know about without going up there, what do we know about capacitors in series? What can we do to them? Yep, excellent, right? That's one thing. What's another thing that we must know about capacitors in series? Voltages add up, excellent. One more thing. Charge is equal. Q1 must equal Q3. The charge must be conserved. It's similar like the current, right? So as I go through capacitors in series or resistors in series, the charge must be conserved because the charge is not being split up. If I have 7 amps or 7 coulombs, as I go from 1 to 3, there's no additional branching, there's no redistribution of the charge or the current. The charge must stay the same. So Q1 is equal to Q3, right? We can figure out this pseudo combined capacitor by taking 1 over C1 plus 1 over C3, and that's equal to 1 over C series, right? Or 1 over C13. We can just call that C13 as the combined capacitor, right? And then we know that branches of capacitors, right? Capacitors in parallel will have the same voltage, right? And capacitors in series will have their voltages add up. So V1 plus V3 is equal to some voltage. What is this voltage going to be equal to? V1 plus V3. Yes, excellent. Why is it equal to 12? Excellent, excellent, excellent. So we can't quite say C1 is directly parallel to C2 at this point, right? Because we also have this C3 here. So we can only say things are parallel to each other, or, series with each other or whatever, right? If we're like, I guess, if there's no other like quote unquote like competition or anything else like involved in the situation. So the other thing that we have involved here is C3, right? So I can't just simply like do 1 over C, or I can't just say like C1, what was it? C1 plus C2, those are in parallel, awesome, done, right? Because I have the C3, what am I going to do with it, right? I have to simplify each and every branch down by itself, if it has like, if there's other components within a branch, right? So this is one branch, this is another branch, right? Along this second branch here, you have resistors or capacitors, in this case, in series, right? So I have to simplify that down first, and then I can say that that combined resistor C13, or this combined capacitor C13, is in parallel with C2, right? I can then say that. And so that is an excellent explanation, because effectively we want the capacitors in parallel to have the same voltage. C2 has to have the same voltage, right? C2 voltage. That branch has to equal the second branch. That second branch is made up of C1 and C3, right? So C1 voltage plus C3 voltage, right? And we can just simplify this down to saying, well, C1, or not C1, V1, right, voltage across 1 plus the voltage across 3 should equal the voltage across 2, right? And then that should equal the 12 volts. And remember, the idea of a resistor is that it's supposed to be dropping the voltage, right? So since we don't have any like resistors here that would drop or detract from the voltage, it's just going to be equal to the voltage of the battery, right? So V1 plus V3, because they're in series capacitors add up the voltages, right? And you add up the resistors, add up the reciprocal of the resistors, right? Or the capacitors. I don't know, I keep saying resistors. Add up the reciprocal of the capacitors, and you add up the voltages of the capacitors in series. So V1 plus V3, add those up. That should equal that combined combined capacitor would be in parallel with C2. And then things in parallel with one another would have to have the same voltage. And that voltage, given that there are no resistors in the circuit, that would decrease the voltage, which is simply be equal to the voltage of the battery. So V1 plus V3 is equal to V2 is equal to 12 volts, right? Now, we're trying to figure out the charge stored in each capacitor here, right? We want to figure out Q1, Q2, Q3, and all of that, right? So we know that Q1 has to equal Q3, because they're in series, so the charge must be conserved, like the current must be conserved, because there's no splitting up or distribution of the current or the charge, right? Q1 is equal to Q3, we already defined that. V1 and V3 have to add up to each other. And then V1 and V3 combined have to equal V2, and that has to equal 12, right? So C3, let's see, that's 4 microfarads, right? So if we look at this equation, V1 plus V3 equals V2, we know that Q equals C over, or Q equals CV, my bad. Q equals CV, right? So V is equal to Q over C. So V1 plus V3 equals V2 can be simplified down to Q1 over C1 plus Q3 over C3 is equal to Q2 over C2, right? Or in other words, it's just simply just be equal to 12, right? Because we said V1 plus V3 with V2 equals to 12 volts, right? If you do that, and you know that Q1 is equal to Q3, then you can just simplify this down to as 2 Q1 over, actually no, I can't. Why do that? I don't think. Or you could, but I mean, anyway, Q1 plus Q1 over C1 C3 like that, right? And C1 and C3 are the same anyway because there's 4 times 10 to the negative 6 farads, right? And that's equal to 12 volts. So because C1 is equal to C3, we can also say, actually, you know what, just rewrite it here at the bottom. So this is 2Q1 over C1 because C1 is equal to C3, right? And that's equal to 12 volts. And so now you can figure out what Q1 is because you have C1. You know that C1 is equal to 4 microfarads, which is 4 times 10 to the negative 6. Actually, I'll just, there, 2Q1 over 4 times 10 to the negative 6 farads is equal to 12 volts. So Q1 is equal to 2.4 times 10 to the negative 5 coulombs, right? That's our Q1. And we know that Q3 is equal to Q1. So this is equal to Q3 as well, right? And now we know that charges for capacitors in parallel, the charges have to be added up, right? So in this case, right, what was I going to say? What did I want to do here? I don't know why I just lost my train of thought. Okay. Okay, oh man. Okay, Q1 equal to Q3, that's fine. And then, okay, so we know that obviously from the beginning that Q is equal to CV. So we want to find like Q total, what that is. So that would be equal to C total times the voltage. So we need to simplify the capacitors down now, right? So C1, C3, we can simplify those down because those are in series. So we do what? We add up the reciprocals of the capacitors. So C1 1 over C1 plus 1 over C2 equal to 1 over C12. So 1 over 4 plus 1 over 4. That gives us 2 over 4, right? And that's, that would just be 2 4, right? And so C12 would just be equal to 2, right? C12 is just equal to 2 at that point. 2 microfarads. And then that is our, or not, my bad, not C1 and C2, C1 and C3. Those are the ones in series, my bad. C1 and C3. And then we have C1, C3, right? And then C13 plus C2, those are connected in parallel. And you add those up, right? Because they're in series. And so you would just have 2 microfarads for this one, right? And then 4 microfarads for the other one, right? So 2 plus 4, that's 6 microfarads. So that's 6 microfarads for the overall. Unless I'm missing something here. I don't know why I'm like I've lost it. So 2 microfarads is the overall. Yep. 2 4 2. Yep. Okay. Yep. Should be 6. That's fine. 6 microfarads is the overall capacitance. Yeah. And then it's just 6 times the negative 6. And that multiplied by your 12 volt there. And your Q total. That's how you figure out your Q total. And let's see here. So I think if you were to figure out your Q total like that, you get like 7.2 times 10 to the negative 5. That's your Q total. And your Q total, like I said, with capacitors in parallel, everything has to add up. Charge has to be conserved, right? So 7.2 times 10 to the negative 5, your Q total would have to be equal to the Q across capacitor 2 and across that second branch made up of C1, C3. Right? Because C1, C3, Q1 equals Q3 will have the same charge across them. So it's like saying Q13 plus Q2, right? And we already said that Q1 and Q3 would be equal to each other. And so Q13, that combined, would just have the same charge. So that's that 2.4 times 10 to the negative 5, I believe, right? So 2.4 times 10 to the negative 5, that's your Q13, and then plus Q2, and then that should give you, let's see here. What was it? 4.8 times 10 to the negative 5 for Q2? Did I do something wrong? I think yeah. Hold up. I've done something wrong here. Oh, I think I see what I did. Or no. Never mind. One sec. Oh, man. Okay, I don't see what I've done wrong here. I don't know why that's not matching up with the key that I have. So, yeah, capacitors in parallel should simply add up to each other. So C3 and C1 is just 1 over 4 plus 1 over 4 is 1 over 2, so you have 2 for that one. 2 plus another 4. Oh. No, wait, hold up, yeah. That's fine. So that's 2 plus 4 to get my overall capacitance. That's 6 microfarads. And 4 times 10 to the negative 6, and then times 12. Oh. No. Never mind. Yeah, I'm not sure what is going on here. Okay, wait a minute. Yeah, I was just trying to add up the capacitors together to figure out the total capacitance. And let me go back here and just edit this here real quick. So I figured out Q1. Alright, screw it. Hold up. I've done something wrong along the way. I'm just not sure what, and so I'm just to be safe, I'm just gonna redo it here. I don't know if I made a calculator error or what I did wrong. Okay, so Q1 is equal to Q3. Yep. We added up the capacitors in parallel. We did, or capacitors in series. We did 1 over C1 plus 1 over C3. So okay, you know what? I am going to erase the whole freaking problem. Just so I start over with a fresh mind, because otherwise I'm just going to confuse myself more. Okay. So C1 and C3, those are in series. Together they should have a voltage of 12 volts, right? We said that V1 plus V3 is equal to V2, and that's equal to 12 volts, all right? Now, if we wanted to figure out the charge across just capacitor 2, the charge across capacitor 2, right? Q equals CV. So we have our capacitor 2, that's 4 times 10 to the negative 6 farads, and then times the voltage, right? That should just simply be equal to, what? 4 times 10 to the negative 6 times 12. Should give us 4.8. Is that 4.8 times 10 to the negative 5? No. See, I don't know. What am I doing wrong here? Oh. I see what I'm doing wrong. Oh my god. No. Like, everything I've been doing is making sense. I just forgot one really important thing. Is that capacitor 2 has a dielectric in it. That's what I've been doing wrong. I forgot that there's a dielectric in between them. I've been trying to use the original capacitance. Okay, that makes a lot more sense now. So it's not 4 times 10 to the negative 6 farads. It should be 8 times 10 to the negative 6 farads, because that's the new capacitance with the dielectric in between. That's kind of bogus that they didn't reiterate that for that problem. But yeah. So this should make more sense now. 8 times 10 to the negative 6. That's your C2, Q2 there. So that gives you 9.6 times 10 to the negative 5 coulombs. Okay, that works. And we can do the same thing we did for V1, V3 earlier, where we did Q equals C over V, Q equals CV. So V equals Q over C. So Q1 over C1 plus Q3 over C3 is equal to 12 volts, right? And then we know that Q1 is equal to Q3. All right, so Q1 plus Q1 there. And we know C1 and C3 just so happen to be the same. So 4 times 10 to the negative 6 farads and 4 times 10 to the negative 6 farads, right? So, and that's equal to 12 volts. So this is just 2Q1 over 4 times 10 to the negative 6 farads equals 12 volts. And then we can figure out the Q1, and that is 2.4 times 10 to the negative 5. What I was doing earlier, where I was doing like C total and Q total and whatnot, that was perfectly okay, and that was like completely right. It's just I completely just overlooked that that capacitor has dielectric in between it. That was my issue. Sorry about that. So that was the main issue there, that the capacitor had a dielectric in between. Does that make sense now? I think this way is probably just a little bit easier. Is to figure out capacitor 2 first, because we know that one is 12 volts for sure, and we can figure that out easily. And then do the second part. Does that make sense? Okay. Last problem, problem 10. Part A. Complex circuit. Consider the circuit pictured. It says determine the value of the current out of the battery. Determine the value of the current out of the battery, right? So we have this battery. Looks like this. And we have another loop like that. We have a resistor here, battery there up top, another resistor here, another resistor there, another resistor here, right? So they're trying to ask us to find the value of the current out of the battery, right? So what you notice here is that they have 1 amp going through here and 2 amps going through there. So remember what we said about tracing the current? So if we start off here, positive terminal, we move through, we trace. What is this called? Informally, like there's no, like they never really defined it, what it is in the book. That's what I defined it as. What do we call that? The branch, right? The branching point. And so that branch, right, means what to the current? What happens to the current in that branch? Current splits, right? So we started off with some amps, and it got split off into 1 amp, split off into 2 amps. So what do you think that current that came out of the battery was? Exactly, right? So I current is equal to I1 plus I2. So 2 amps plus 3, or 1 amps. Yeah, I think I got it the other way around. 1 amp plus 2 amps is 3 amps, right? And so that's the current there, right? And this is based on the junction rule that was found at the end of chapter 11's reading. That's the junction rule, where I'm stupid actually. That's what it's called, not a branch point, a junction. But branch point, like I think that just makes more sense, like tree branches and stuff. But yeah, that's a junction or a branch. B says determine the voltage of the battery, right? We know that when you go across resistors, the voltage drops, right? So if we start off with 12 volts, you go through a resistor, it takes away some voltage, takes another voltage, takes another voltage, the voltage drops, right? So V battery minus the voltage across each resistors, like resistor 1 minus resistor 2 minus resistor 3, all that should equal 0. Because it's like 12 volts, voltage drop of 2 volts here, maybe a voltage drop of 3 volts there, minus 4 volts here, whatever, right? That's the idea here with voltage drops. And so you have V battery, right, minus, what was I going to say? Yeah, okay. So first of all, before we go into this, right, there's a loop rule, right? There's a Kirchhoff's loop rule. So the loop rule tells us that basically through a specific loop, right, or kind of a connection in a circuit, right, through one loop, what we observe is that like total change in the energy from starting off at the positive terminal of the battery to the end of the battery should be 0. And at the same time, right, the voltages in a loop, in a specific loop, the voltages in a loop must add up to each other, right? To where that if I were to pick any single loop, right, any one loop, then the voltage drop should add up to each other, energy is conserved, right, all of that, and you have a change in voltage that's equal to 0, right? So the idea is that the change in voltage is equal to 0, where that you have your voltage drops across each of those resistors equal to the voltage of the battery that you started off with, right? So like V battery, like I said, V battery minus the voltage drop across resistor 1 minus the voltage drop across resistor 2, etc. Those should equal 0, right? So here, the loop that we have you can pick one of two loops. You can either pick this huge loop, which is more complex, if you will, because essentially you would go through this resistor, then through that resistor, and then through this resistor, and then back to the battery. That's one loop, right? Then you'd have to add 3 resistors in series, as opposed to this loop, where it goes this resistor, then this resistor, and then back to the battery, right? That's much simpler. The idea is that you go through one loop, right? It's almost like saying you pick one branch, and you go through it, and that's it, right? You pick one loop, or this loop, right? And you go through it, and you figure things out. So through this loop here, right, we have, this is 20 ohms, and this is 60 ohms, right? And we know that the current that was released by the battery was like 3 amps initially, right? So we have V battery minus the current going through resistor, let's call this resistor 1 over here. This is resistor 1, this is resistor 2, right? So minus the current going through resistor 1, I say I1, and this is, well, I don't want to say I1, oh yeah, I can actually, I1 times resistor 1, minus the current going through resistor 2 times resistance of resistor 2, right? So what do you notice about the current going through resistor 2? What's the value of that current? 1, right? So just because you pick this loop doesn't mean that you're like considering that to be the only thing there. We still are feeling the effects of this branch point, right? To where you had 3 amps going in here first. 3 amps goes through R1. 1 amp gets split off to go to R2, and then 2 amps goes split off into these other resistors here, right? And so I1, which is R1 here, right? That current would be what? What would be the current going through that first resistor? Three amps, right? Because it's perfectly conserved, unadulterated, no branching in between the battery and R1. So it gets that full 3 amps before it branches out anywhere else. And that's times 20 ohms, right? And the V battery, right? Well, that's what we're trying to figure out. V battery minus all this is equal to 0. That's the loop rule. So V battery is actually equal to 3 times 20 plus 1 times 60. And you can see that that's 60 plus 60, and that's 120 volts for the battery. Make sense for B? Okay. Finally, for C, it says determine the equivalent resistance of all 4 resistors. So just basically just adding up all the resistors together, right? Simplifying them down into one equivalent resistor. So what resistors, this is a test for you guys now. Show me what you learned. So actually, you know what? Let me just draw something over here. I'll draw the resistor again here, the circuit, I mean, in a cleaner way. You have the battery, right? There is our resistor here, resistor there, resistor here, this is 20 ohms, resistor there, 60 ohms, 20 ohms, 10 ohms, right? And then what else? I think that's it, right? Oh yeah, R1, R2, R3, R4. Okay. So, what's in parallel with what? What's in series with what? We can take it step by step. Excellent. R3 is in series with R4. So we just take R3 plus R4, right? So that's just going to be 30 ohms, right? So now we've simplified it down into this pseudo resistor called R34, 30 ohms. Okay, what's next? R1, R2 in parallel. No, not quite. And they're not quite in series either, because there's branching between R1 and R2, but they're not branched with each other, right? Exactly. R2 and R34 are parallel with one another, and then R234 is in series with R1. So R2 and R34, so R34 is this combined resistor. R2 and R34 are parallel with each other, right? When you combine them, R234 is in series with R1, right? Because, exactly. No, you're right. Because once you go through, you have this branching point, right? This branching point, the branches that stem off of it after that branching point are the branches that are in parallel with one another, right? The resistors that are in parallel with one another. But anything that comes before it is not in parallel necessarily or in series with the rest of the branches. You have to then simplify this first. You have to simplify the branches down first. Then you can figure out if this resistor is in series or in parallel with the rest. Does that make sense? Yeah, exactly. Mm-hmm. Mm-hmm. Exactly. Exactly. Mm-hmm. Yeah. Yeah. No, it doesn't. It doesn't matter. It doesn't matter like the location that you put them in. Like I could very well just have said R34 is over here. That's the same. But you do realize that still this is a branch and this is a branch, and because they're in branches, they're still in parallel with one another. So it's like the location where you put them is not. Yeah, the location where you put them doesn't matter. It's just that you still have to recognize that R2 and R34 are still in parallel with one another because they're branched off. They have split currents between them. Mm-hmm. But yeah, I mean, look, once you get to the branch point, anything after, they're going to be in parallel with one another. Anything before, you can't quite say it's parallel or series until you simplify what comes after. Because it's like I said, with the tree trunk, you have this. Here is that R1, right? Here's the branch coming off, right? If R2 was here along that branch, then we could say it's in series. But it's not. That's not where the branch is located. Instead, this is what happens. Here is R2, right? And then there might be, let me try and think about this. So, yeah. And then R3 and R4 on the same branch, like that. So R3 and R4 are on the same like sub branch. Like this is branch. This is sub branch. And so R3 and R4 are on the same sub branch, so you can combine them together. They're in series. But then R3, 4, and R2 are in different sub branches. You have to recognize that those are in parallel with one another. They're not connected consecutively, because it's like, oh, I have 3 amps here. 3 amps would go normally through this branch, but instead it's like 2 amps here, 1 amp there. Right? So now I have to combine those two sub branches to be in parallel with one another, or to simplify them down. That's what I mean. So now you get rid of this sub branch. It's like you cut it off, right? Now you have this one big branch that's R2, 3, 4, and then that's consecutive in series with R1. Does that make sense? Do you see that? Or is that like, I don't know how helpful that analogy is. Okay, awesome. Like, it makes more sense to like look at trees than to look at circuit diagrams. Um, yeah, but in that sense, right, you can then simplify the R2 and R3 4 pseudo resistors going to be like they're going to be in parallel with one another once again, and so you have to simplify them down. We can add resistors in parallel by taking the sum of the reciprocals. So 1 over 60, right? 1 over 60 plus 1 over 30, right? And then that's 2 over 60, 3 over 60, 1 over 20, right? And that's equal to 1 over 2, 3, 4, right? So in order to get like 1 over 20 is equal to 1 over that pseudo combined resistor R234. R234 is then just equal to, if we just multiply it over and then multiply this over, right? R234 is equal to 20 ohms, right? And so then we're left with R234 as 20 ohms, this overall combined resistor, right? And so that's going to be in series with R1. So 20 plus 20, 40, right? So R equivalent, or R1234 is equal to 20 ohms. R234, or equal to 40 ohms, my bad. Because it's 20 plus 20. R234 is 20 ohms. And then, yeah, this is essentially what you're trying to reach. You're trying to reach the overall equivalent combined pseudo resistor for all of them together. R1, 2, 3, and 4 is equal to 40 ohms. The goal is to simplify everything down to where everything is just in series with the battery. Does that make sense overall? Okay. Did I clear up confusion with circuits, capacitors, all of that stuff tonight, or we still having trouble? Like, I mean, obviously, like, we're still going to do a practice exam tomorrow and the day after, so like there's still time to figure things out. But did a lot of I hope a lot of, or at least some of, like your issues have been solved with the review session tonight. Okay, awesome. But yeah, if there aren't any other questions, I'm gonna go ahead and end the recording here, and then have this uploaded, and try to do the transcript thing that I was talking about, so it'll upload to Google Drive as well. But yeah, that's the recording, and then I can stay after like a minute or two just to see if there are any other questions. But I have to go break my fast, so I'm very hungry. But yeah, that's the end of the recording.